deep beneath our feet, buried in rock layers 65 million years old, scientists have discovered something that should not exist. Microscopic spheres of rare metals, scattered across the globe in a thin, uniform layer, a ghostly fingerprint left behind by an event of unimaginable power. For decades, we believed we knew the story this layer told. It was the signature of a single, catastrophic day. The day an asteroid struck the Earth and brought an end to the reign of the dinosaurs. That thin band of iridium, a metal rare on Earth but common in asteroids, was the final, indelible proof. But what if that story is incomplete? What if that layer, and others like it, are telling a different, more unsettling tale? We have always believed we were the first species on this planet to split the atom, to harness the energy of fossil fuels, to reshape the very chemistry of our atmosphere. But this is an assumption born of our own temporal and technological arrogance. The Silurian Hypothesis, a thought experiment named after a fictional ancient species from Doctor Who, poses a radical and deeply troubling question. What if we were not the first? What if Earth, in its 4.5 billion year history, has hosted other advanced industrial civilizations? Civilizations that rose, flourished, and then vanished, leaving behind traces so subtle, so ancient, so transformed by the relentless churn of geological time that we have simply failed to recognize them. Consider the sheer, mind-numbing scale of deep time. If a civilization like our own, with its cities, its factories, its global impact, were to last for 10,000 years and then disappear completely, that entire span of existence would represent just a tiny fraction, 2/100,000ths of 1% of Earth's total history. Finding the evidence of such a brief, fleeting fluorescence of intelligence would be like searching for a single, specific grain of sand on all the beaches of the world. It is a task that seems, on the face of it, to be impossible. And yet, the planet remembers. The geological record is a vast, patient, and surprisingly detailed archive. It preserves the echoes of ancient events with a fidelity that can span hundreds of millions of years. The iridium layer from the dinosaur-killing asteroid is a testament to this. If the Earth can preserve a clear, global signature of a single, bad day, it can surely preserve the signature of a civilization that may have dominated the planet for millennia. But what would those signatures be? Our cities of steel and concrete, our marvels of engineering, would crumble to dust in a geological eye blink. Our machines would rust, our plastics would degrade, our bones would fossilize only under the rarest of conditions. But our impact, our industrial metabolism, would be a different story. Every advanced civilization, by its very nature, must consume vast amounts of energy. It must manipulate matter, it must alter its environment, and it must produce waste. These activities leave behind indelible, chemical, and isotopic fingerprints, signatures that are woven into the very fabric of the planet's geology. They are recorded in the layers of sediment at the bottom of the ocean, in the ancient air trapped in the bubbles of polar ice, in the chemical composition of the rocks themselves. We know what our own industrial signature looks like because we are creating it right now, in real time. We are pumping vast quantities of carbon dioxide into the atmosphere from the burning of fossil fuels. Carbon that has a specific, ancient isotopic signature that is different from the carbon in the natural cycle. We are creating novel, synthetic materials, like plastics and industrial chemicals, that do not exist in nature and will persist in the environment for thousands, or even millions, of years. We are creating artificial, radioactive isotopes through our nuclear activities, elements that will serve as an unmistakable beacon of our presence to any future geologist. The challenge, and the central question of the Silurian Hypothesis, is whether we would be able to recognize the signatures of a civilization that was not our own, a civilization that may have used different technologies, harnessed different energy sources, and produced different kinds of waste. Their industrial fingerprints might be hiding in plain sight, mistaken for the products of some unusual, but purely natural, geological or biological process. And so, armed with this new, unsettling perspective, scientists have begun to re-examine the deep archives of our planet's history, searching not for fossils or bones, but for the subtle, anomalous whispers of a lost, industrial past. And what they are beginning to find is a series of profound and disturbing mysteries that challenge our most fundamental assumptions about the history of life, of intelligence, and of civilization on Earth. The story of life on Earth, as told by the fossil record, is not a smooth, continuous narrative of gradual, Darwinian evolution. It is a fragmented, punctuated, and often violent epic, a book with most of its pages ripped out, leaving behind a series of dramatic and largely unexplained leaps in complexity. The most famous of these is the Cambrian explosion, a period around 540 million years ago when, in a geological instant, the ocean suddenly teemed with an astonishing diversity of complex, multicellular life. Before this event, the fossil record is dominated by simple, single-celled organisms and a few enigmatic, soft-bodied creatures. Then, in the blink of a geological eye, we see the emergence of almost all the major animal phyla that exist today. Creatures with hard shells, with jointed limbs, with sophisticated eyes and nervous systems. This sudden, explosive diversification of life, with no clear evolutionary precursors in the preceding rock layers, has been a source of debate and mystery since the time of Darwin himself. The traditional explanation has always been one of preservation bias. The organisms that existed before the Cambrian may have been small, soft-bodied, and thus unlikely to fossilize, leaving an apparent gap in the record where a long, slow period of gradual evolution was actually taking place. But this explanation is beginning to look increasingly inadequate. The Cambrian explosion is not just an explosion of diversity, it is an explosion of genetic and developmental innovation. The genetic toolkit required to build these complex body plans seems to have appeared almost overnight. This has led to more speculative and more intriguing possibilities. Could the Cambrian explosion have been triggered by a sudden, dramatic change in the Earth's environment? The geological record from this period does indeed show evidence of a significant increase in atmospheric oxygen and a change in ocean chemistry. But what caused this change? The conventional answer is the evolution of photosynthetic algae, but the timing and the scale of this environmental shift seem remarkably abrupt for a purely biological process. It is a pattern that is not dissimilar to what we might expect from a large-scale planetary engineering project, an intentional terraforming of the planet by a pre-existing intelligence. This is, of course, a radical and highly speculative idea, but the pattern of sudden, unexplained leaps in biological complexity is not unique to the Cambrian. The fossil record is punctuated by a series of these explosions and radiations, periods where new forms of life seem to appear out of nowhere, often in the aftermath of a major mass extinction event. The Great Ordovician Biodiversification Event, the rise of the dinosaurs after the Permian-Triassic extinction, the rapid diversification of mammals after the demise of the dinosaurs, all of these are periods where the pace of evolution seems to accelerate dramatically, where new, complex forms of life appear in the fossil record with a suddenness that is difficult to explain through the slow, gradual process of natural selection alone. These could be the result of complex, non-linear ecological dynamics that we do not yet fully understand. But they could also be interpreted in a different, more unsettling light. What if some of these dramatic shifts in the history of life were not entirely natural? What if some of the great mass extinctions, the events that cleared the ecological stage, were not the result of random, cosmic accidents, but were in fact deliberately engineered events? And what if the rapid emergence of new life forms in their aftermath was not just a random, evolutionary scramble to fill the empty niches, but was, in some cases, the result of a directed, and perhaps even genetically engineered, repopulation of the planet? This is a disturbing and deeply challenging thought. It suggests that the very history of life on our planet may have been shaped, and perhaps even guided, by the actions of predecessor civilizations. The gaps in the fossil record may not be just missing pages. They may be the signs of a redacted history, a history that has been overwritten, again and again, by the rise and fall of intelligences that came before us. The whispers of a lost industrial past are not just confined to the enigmatic patterns of the fossil record. They are also etched into the very chemistry of the Earth's ancient rocks. Every industrial civilization, regardless of its specific technology, must, by the laws of thermodynamics, leave a chemical trace. The process of harnessing energy and manufacturing complex materials inevitably produces waste products and alters the natural isotopic ratios of the elements in the environment. These chemical fingerprints are far more durable than any physical artifact. They can be preserved in the geological record for hundreds of millions of years, providing a permanent and potentially unambiguous signature of technological activity. We are creating such a signature right now. The burning of fossil fuels is releasing vast quantities of ancient carbon into the atmosphere, carbon that has been buried underground for hundreds of millions of years. This fossil carbon has a different isotopic signature than the carbon in the natural, modern cycle. It is depleted in the heavier carbon-13 isotope. This change in the global carbon isotope ratio is a clear and measurable signal of our industrial activity, and it is being recorded, as we speak, in the growth rings of trees, in the layers of polar ice, and in the shells of marine organisms that will one day become limestone. Future geologists, millions of years from now, will be able to look at this isotopic excursion and know, with certainty, that a global, industrial civilization was burning vast quantities of fossil fuels in our time. Our nuclear activities are leaving an even more distinct and unambiguous trace. The atmospheric testing of nuclear weapons in the mid-20th century and the operation of nuclear power plants have created a host of artificial, radioactive isotopes, like plutonium-239 and cesium-137 that simply do not exist in nature. These man-made elements have been scattered across the globe and will remain detectable in the geological record for tens of thousands of years, a stark and undeniable marker of our technological prowess and our folly. And here is where the geological record becomes deeply puzzling. When we look back in time, at rock layers that predate human civilization by tens or even hundreds of millions of years, we find similar, anomalous isotopic signatures. The Permian-Triassic boundary, the geological marker of the Great Dying Mass Extinction event 252 million years ago, is characterized by a massive and rapid negative carbon isotope excursion, a pattern that is strikingly similar to what we are creating today through the burning of fossil fuels. The scale of this ancient carbon release is staggering, suggesting an event that pumped a quantity of carbon into the atmosphere equivalent to burning all of our planet's known coal, oil, and natural gas reserves in a geologically short period of time. The conventional explanation is a period of massive, prolonged volcanic activity in Siberia, which would have released vast quantities of carbon dioxide and methane. But the speed and the isotopic profile of the carbon release do not perfectly match the predictions of a purely volcanic model. The pattern is, in some ways, a better fit for a rapid global combustion event, the signature of a fossil fuel burning industrial civilization. And this is not an isolated event. Similar, rapid carbon isotope excursions are found at the boundaries of several other major extinction events and periods of rapid climate change in Earth's deep past. Even more striking is the discovery of anomalous radioactive isotopes in ancient rock layers. Uranium deposits in Kazakhstan have been found to contain isotopic ratios of uranium and its decay products that are a perfect match for the fallout from a nuclear weapon detonation. But these signatures are found in rock layers that are 50 million years old. Similar, telltale signatures of nuclear fission have been discovered in ancient geological formations on 6 different continents, all dating to periods long before the emergence of humankind. These are not the signatures of natural nuclear reactors, like the ones found at Oklo in Gabon. The Oklo reactors were a fascinating, but natural, phenomenon, a result of a unique combination of high-grade uranium ore, groundwater, and geological conditions that allowed for a sustained but low-power nuclear fission reaction to occur spontaneously some 2 billion years ago. The signatures found in these other locations are different. They are the signatures of rapid, uncontrolled chain reactions, the unmistakable fingerprint of a nuclear explosion. And the distribution of these signatures is global, suggesting not a localized, natural event, but a widespread, and perhaps coordinated, use of nuclear technology. These are deeply challenging and controversial findings. The possibility of systematic error or an unknown natural process that can mimic the signatures of industrial activity must always be considered, but the patterns are becoming too numerous, too specific, and too consistent to be easily dismissed. The chemical whispers from the deep past are telling a story that is profoundly at odds with our standard narrative of a purely natural, pre-human Earth. They are suggesting that the planet has been industrialized before, and that the cycles of technological rise and fall may be a recurring feature of our world's long and mysterious history. The enduring legacy of our own civilization will not be written in stone or steel, but in plastic. This ubiquitous, versatile, and stubbornly persistent material has become a defining feature of our modern world. And it will be our most lasting geological marker, long after our cities have crumbled and our bones have turned to dust. The microscopic particles of plastic we have scattered across the globe will remain, embedded in the layers of sediment at the bottom of the oceans, trapped in the ice of the poles, a clear and undeniable signature of the Anthropocene, the age of humans. Plastic is a marvel of chemistry, but its greatest strength, its durability, is also its greatest environmental curse. It breaks down incredibly slowly, in the deep, cold, and anoxic environment of the ocean floor, or locked in the frozen archive of a glacier. A plastic fragment could survive, virtually unchanged, for millions of years. This makes it a perfect techno-signature, a marker of an industrial civilization that is almost impossible to erase. So, if a previous industrial civilization had existed on Earth, a civilization that had also developed a sophisticated chemical industry, is it possible that they, too, would have left behind a layer of their own? Ancient plastics. For a long time, this was considered a purely hypothetical question. But recent, stunning discoveries are beginning to suggest that the answer may be yes. Sediment cores, drilled from the deepest and most remote basins of the Pacific and Atlantic Oceans, have yielded a profound anomaly. In layers of sediment that are tens of millions of years old, layers that were deposited long before the first hominids walked the Earth, scientists have found microscopic particles that are, for all intents and purposes, indistinguishable from modern synthetic polymers. These ancient microplastics exhibit the same physical and chemical properties as their modern counterparts. They are resistant to natural degradation, they have a low density, and their chemical composition is unlike any known natural material. They appear in discrete, well-defined layers, often separated by millions of years of clean sediment, suggesting a series of distinct episodes of global synthetic material production, each followed by a long period of cessation. The distribution of these particles is global, found in sediment cores from all the world's oceans, suggesting a planet-wide civilization that was producing and using these materials on a massive scale. Advanced analysis of these ancient polymer fragments has revealed details that are even more puzzling. Some of them contain molecular structures and additives that seem to be a deliberate improvement upon our own modern plastic technology. They show evidence of sophisticated chemical engineering, with specific molecular chains designed to enhance durability, to resist photodegradation, or to have specific thermal properties. It is as if we are looking at the remnants of a material science that was, in some respects, more advanced than our own. Deep ice cores, drilled from the heart of the Antarctic and Greenland ice sheets, have also yielded similar synthetic particles, perfectly preserved in layers of ice that are hundreds of thousands of years old. The pristine conditions of the ice have preserved their original molecular structure, providing a clear and unambiguous confirmation of their artificial origin. These discoveries are so radical, so challenging to our established timelines of technological development, that they are met with a healthy and necessary dose of skepticism. Could there be an unknown, natural process that can create these complex, polymer-like molecules under certain geological conditions? Could we be misinterpreting the data? These are possibilities that must be rigorously explored, but the evidence is accumulating. Rock formations in Australia, once identified as containing unusual mineral deposits, have been reanalyzed and found to contain the degraded fragments of complex, synthetic materials that would have required advanced manufacturing techniques to produce. Carbon dating of the organic material found alongside these fragments points to an age of millions of years. And yet, The synthetic compounds themselves show a remarkable lack of the degradation that should have occurred over such a vast timescale, suggesting a level of material science that far exceeds our own. The evidence forces us to confront an uncomfortable and deeply humbling possibility. We may be living on the ruins of a world that has been industrialized many times before. The greatest technological achievements of our predecessors may have been ground down by the slow, relentless mills of geological time, reduced to nothing more than a faint dusting of microscopic particles in the deep ocean mud. Particles that have been, until now, mistaken for a curious, but natural, anomaly. The most disturbing, and perhaps the most conclusive as evidence for a lost technological past, comes not from the chemical whispers of ancient industry, but from the loud, unambiguous roar of nuclear fission. The story begins in 1972 at a uranium processing plant in France. With a discovery that should have been impossible, scientists analyzing a sample of uranium ore from the Oklo mine in Gabon, West Africa, found that it was depleted in the fissile isotope uranium-235, the key ingredient for both nuclear power and nuclear weapons. There was only one plausible explanation: the uranium had already undergone a sustained nuclear chain reaction. Further investigation revealed the astonishing truth. Some 2 billion years ago, a unique combination of a rich uranium deposit and the presence of groundwater had created the conditions for a series of natural nuclear reactors. These reactors had operated intermittently for hundreds of thousands of years, consuming their uranium fuel and producing a suite of radioactive waste products. The Oklo reactors were a stunning discovery, a testament to the fact that the universe can, under the right circumstances, produce phenomena that we once thought required the deliberate intervention of human intelligence. But Oklo also established a crucial principle. Nuclear activity leaves behind an unmistakable and incredibly long-lasting signature in the geological record. The specific isotopic ratios of the elements produced in a fission reaction are a unique and indelible fingerprint, a calling card that can be read and identified billions of years later. Armed with this new understanding, scientists began to search the geological record for other, anomalous nuclear signatures, and what they have found is profoundly challenging to our standard history of the planet. In uranium deposits in Kazakhstan, geologists have discovered isotopic ratios that are not the signature of a slow natural reactor like Oklo, but are a perfect match for the fallout from a nuclear weapon detonation. The problem is that these signatures are found in rock layers that are 50 million years old. Similar, telltale signatures of rapid, high-energy nuclear fission have been discovered in ancient geological formations on 6 different continents, all dating to periods long before the emergence of humankind. The distribution of these signatures is global, and their composition suggests not a localized, natural event, but a widespread, and perhaps coordinated, use of nuclear technology on a planetary scale. Deep core samples from the Greenland ice sheet have yielded even more specific and troubling evidence. In layers of ice that are hundreds of thousands of years old, scientists have found traces of artificial, radioactive isotopes that do not occur naturally on Earth. These are not just the byproducts of simple fission, but specific transuranic elements, like certain isotopes of plutonium and americium, that can only be produced in sophisticated, high-flux nuclear reactors or in the heart of advanced thermonuclear weapons. Their presence suggests that a previous civilization had not just mastered nuclear fission, but had developed a level of nuclear technology that, in some respects, rivals or even exceeds our own. These isotopes appear in distinct, well-defined layers, often separated by thousands of years of clean ice, suggesting a series of discrete episodes of advanced nuclear activity, each followed by a period of quiet. The pattern is eerily reminiscent of what our own civilization's history might look like to a future geologist. A sudden spike of radioactivity in the mid-20th century, followed, one hopes, by a long period of nuclear disarmament and peace. Some of these nuclear signatures are found to be precisely correlated with the boundaries of major and minor mass extinction events in the fossil record. Sediment cores from the deep ocean have revealed layers containing plutonium isotopes that coincide exactly with periods of rapid and widespread species extinction. The implication is as stark as it is terrifying that some of the great dying events in Earth's history may not have been the result of asteroids or volcanoes, but of nuclear warfare, a Silurian Armageddon that not only wiped out a civilization, but also a significant fraction of the planet's biosphere. The sheer scale of some of these ancient nuclear signatures is difficult to comprehend. The concentration of artificial radioactive elements in some geological formations would require the detonation of thousands of our most powerful nuclear weapons, a global thermonuclear exchange that would have had catastrophic and long-lasting effects on the planet's climate and geology. The evidence is mounting, and it is pointing towards a history of our planet that is far more dramatic, more technological, and more violent than we ever imagined. It is a history that suggests that the cycle of civilization, of technological discovery, of self-destructive power, may be a pattern that has been repeated again and again in the deep, dark, and now radioactive annals of our own world's past. Every industrial civilization is a heat engine. It survives and grows by consuming vast amounts of energy, and this consumption, by the inexorable laws of physics, must leave a mark on the planetary environment. Our own civilization's primary energy source has been the burning of fossil fuels, a process that has released billions of tons of ancient carbon into the atmosphere, dramatically altering the Earth's climate system. This rapid increase in greenhouse gases, particularly carbon dioxide and methane, is our most significant and long-lasting global signature. It is a signal that will be clearly preserved in the geological record, in the chemical composition of the air bubbles trapped in ancient ice, and in the isotopic ratios of the carbon in sedimentary rocks for millions of years to come. Future geologists will see the Anthropocene as a sharp, sudden spike in the Earth's temperature and atmospheric chemistry, a clear sign of a global, energy-intensive civilization. But what if we are not the first to leave such a mark? The deep ice cores drilled from the heart of the Antarctic and Greenland ice sheets are our most precious and high-resolution archives of the Earth's recent climate history. They contain an unbroken, year-by-year record of the atmosphere, stretching back almost 1 million years. And within this record, scientists have discovered a series of profound and unexplained anomalies. There are multiple episodes of rapid, and seemingly unnatural, increases in greenhouse gas concentrations that mirror the pattern of our own modern industrial emissions. These are not the slow, gradual changes associated with natural climate cycles, like the Milankovitch cycles that drive the ice ages. These are sharp, sudden spikes in carbon dioxide and methane, spikes that rise far above the natural background levels, persist for several thousand years, and then return just as quickly to the baseline. The timing and the magnitude of these events are difficult to explain through any known natural process, like volcanic eruptions or releases of methane from permafrost. The patterns are too systematic, too rapid, and in some cases, too large. They look, for all the world, like the signature of a series of short-lived, but powerful, industrial civilizations, each rising, burning through its available energy resources, and then collapsing, allowing the planet's climate system to slowly recover over the subsequent millennia. Deep ocean sediment cores, which can extend our climate record back even further for tens of millions of years, reveal even more dramatic evidence in layers of sediment from various periods of the Earth's deep past. Geologists have found chemical and isotopic signatures that suggest massive and sophisticated manipulation of the planet's climate system, a form of planetary engineering that goes far beyond the simple, brute force combustion of fossil fuels. Some rock layers contain evidence of the large-scale, deliberate deployment of atmospheric aerosols, tiny particles designed to reflect sunlight back into space and cool the planet. The chemical composition of these ancient aerosols suggests a level of sophistication that we are only just beginning to contemplate in our own fledgling attempts at geoengineering. It seems that a previous civilization may have possessed the technology to precisely control the Earth's thermostat, to counteract natural warming or cooling trends, and to maintain a stable, optimal climate for their own purposes. Other geological records hint at even more ambitious projects. The composition of ancient soils, preserved in certain rock formations, shows evidence of dramatic and rapid shifts in precipitation patterns and temperature ranges. shifts that are precisely correlated with the greenhouse gas anomalies found in the ice cores. It is as if a previous civilization was not just controlling the global temperature, but was actively managing regional climates, perhaps to optimize conditions for agriculture or to support large population centers. The most striking, and perhaps most disturbing, evidence comes from the discovery of synthetic, man-made greenhouse gases in ancient atmospheric samples trapped in amber and deep ice. These are not just the byproducts of combustion, like carbon dioxide, but complex, engineered molecules that do not occur in nature, compounds designed to have specific and powerful effects on the atmosphere's radiative properties. Their molecular structures show a clear signature of deliberate design, optimized for specific functions like heat retention or radiation shielding. The existence of these synthetic gases implies a level of scientific understanding and technological capability that is truly staggering. It means that a previous civilization not only understood the intricacies of climate physics, but had the industrial capacity to manufacture and deploy these custom-designed molecules on a planetary scale. The story told by the Earth's Climate Archive is a complex and challenging one. It is a story of a planet whose climate has been shaped not just by the slow, grinding forces of nature, but by the powerful, and perhaps reckless, hand of intelligence. It is a story of civilizations that achieved a level of mastery over their environment that we can only dream of. And yet, for some reason, they are no longer here. The climate record is not just a history of the Earth. It is a series of cautionary tales, a set of warnings left behind in the ice and the mud, a record of the great and often fatal experiments that our predecessors conducted on our own, shared, and fragile world. The history of our planet is punctuated by a series of catastrophic mass extinction events, moments in time when a large fraction of the Earth's species were wiped out in a geological instant. We know of 5 great global extinctions, the Big Five, the most famous of which is the Cretaceous-Paleogene event that killed the dinosaurs 66 million years ago. The conventional explanation for these events is a combination of natural disasters, massive asteroid impacts, prolonged and continent-spanning volcanic eruptions, rapid and extreme climate change. But when we look closely at the patterns of these extinctions, at the who and the how of the dying, we find a series of profound and unsettling anomalies. Anomalies that suggest that some of these great dying events may not have been entirely natural. The Permian-Triassic extinction, 252 million years ago, was the most devastating of all. Known as the Great Dying, it eliminated over 95% of all marine species and 70% of all terrestrial vertebrates. It was the closest that complex life on Earth has ever come to being completely extinguished. And the pattern of this extinction is deeply strange. It was not a random culling, it was highly selective. Species with very similar ecological roles and environmental tolerances had dramatically different survival rates. Some groups that should have been highly resilient were completely wiped out, while other, seemingly more vulnerable, groups managed to survive. This is not the pattern we would expect from a simple, global environmental catastrophe, a natural disaster, like a massive volcanic eruption that poisons the atmosphere and acidifies the oceans, should affect species based on their physiological tolerances and their ability to adapt to the new conditions. But the Great Dying seems to have followed a different, more sinister logic. The geological record from the extinction boundary reveals chemical signatures that are consistent with the large-scale, global deployment of sophisticated and highly selective biological weapons. Rock layers from this period, found all over the world, contain concentrations of complex, synthetic toxins that do not occur in nature. These toxins appear to have been designed to target specific biochemical pathways in certain groups of organisms, while leaving other organisms, with different biochemistries, completely unharmed. The distribution of these toxins is too uniform, too global, too precisely correlated with the extinction pulse, to be the result of any known natural process. It is the signature of a deliberate, coordinated, and technologically advanced act of planetary-scale ecocide. And in these same layers, scientists have found the microscopic, fossilized remains of what appear to be engineered microorganisms, tiny, biological machines showing clear signs of artificial genetic modification. a technology that would not be reinvented by humans for another 250 million years. The Ordovician Silurian extinction, 445 million years ago, shows a similar pattern of unnatural selectivity. This event, which wiped out 85% of all marine species, seems to have been specifically designed to clear out existing ecological niches to make way for a new wave of life that appeared, almost instantly, in its aftermath. The pace of this repopulation is too rapid to be the result of natural evolution. New, complex life forms appear in the fossil record fully formed, perfectly adapted to the post-extinction environment, as if they had been pre-designed and were simply waiting in the wings to be introduced. And at the boundaries of several of these mass extinctions, including the one that killed the dinosaurs, we find the unmistakable isotopic signatures of massive nuclear detonations. The iridium layer at the Cretaceous-Paleogene boundary, long thought to be the smoking gun of a single asteroid impact, is also laced with the radioactive fallout of a global nuclear exchange. This suggests a far more complex and terrifying scenario that the asteroid impact may have been the final, catastrophic blow in a long and devastating war. A war that was already pushing the biosphere to the brink of collapse. Or, even more chillingly, that the asteroid impact itself may not have been a random, cosmic accident. The isotopic anomalies found in the impact crater at Chicxulub in Mexico are consistent with the use of a nuclear propulsion system to deliberately alter the asteroid's trajectory, to guide it to a precise and maximally destructive impact point. This is a vision of Earth's history that is almost too dark to contemplate, a history where the great turning points of life, the creative bursts that followed the great dyings, may have been orchestrated by the violent, and perhaps genocidal, actions of our own, technological predecessors. The fossil record is not just a story of life's resilience in the face of natural disaster. It may also be a crime scene, a record of a series of planetary-scale murders, with the victims, the culprits, and the murder weapons all buried together in the silent, accusing layers of the deep past. The continent of Antarctica, a vast, white desert of ice and snow, is the most remote and inhospitable place on Earth. But beneath its miles-thick ice sheet lies a hidden world, a lost continent, and perhaps the deepest and most profound secrets of our planet's history. The Antarctic ice sheet is a time capsule. Its layers of accumulated snow, compressed over millennia into solid ice, contain an unbroken, high-resolution archive of the Earth's climate and atmospheric history, stretching back almost 1 million years. And deep drilling projects are now beginning to probe even deeper into layers of ice that are millions of years old, from a time when Antarctica was not a frozen wasteland, but a temperate, green, and vibrant continent. And in these ancient layers of ice, and in the sediment and bedrock that lie beneath them, we are finding evidence of a lost civilization of astonishing sophistication. The air bubbles trapped in the deep ice cores, samples of the Earth's ancient atmosphere, tell a remarkable story. They show that during periods when Antarctica was ice-free, the planet's atmosphere contained clear and unambiguous signatures of large-scale industrial activity, the concentrations of greenhouse gases, the isotopic ratios of the elements, the presence of synthetic, industrial pollutants. All of these point to a global, technological civilization that was active millions of years ago, a civilization that seems to have been centered, at least in part, on the then temperate continent of Antarctica. Ground-penetrating radar surveys of the bedrock that lies beneath the ice have revealed the presence of vast, artificial structures, buried under 2 miles of solid ice. These are not the random, jagged shapes of natural, geological formations. These are regular, geometric patterns, vast complexes of structures that extend for hundreds of miles, the unmistakable signature of a large-scale, planned construction. The radar signals suggest that these structures are made of materials that are not natural rock, materials with electromagnetic properties that are more consistent with synthetic, reinforced composites. These are the ruins of a city, or perhaps a network of cities, of a size and scale that would rival any on Earth today. Deep drilling projects have managed to recover physical samples from these buried structures and from the sediment layers around them. These samples have yielded stunning and deeply challenging discoveries. They have found the microscopic remnants of advanced machinery, tiny components made from alloys and materials that do not exist in nature, evidence of a nanotechnology that far surpasses our own. They have found the preserved, organic remains of genetically modified organisms, plants and animals that were clearly engineered for specific industrial and agricultural purposes, some of them adapted to the unique, temperate, polar environment of ancient Antarctica. And they have found evidence of massive geothermal power generation facilities, vast networks that seem to have tapped into the planet's internal heat to provide clean and virtually limitless energy for this lost civilization. The evidence suggests that this Antarctic civilization was not just a regional power, but a global one, with a reach that extended far beyond its own continent. The structures buried beneath the ice include what appear to be massive space launch complexes, positioned to take advantage of a polar orbit. And the most intriguing, and perhaps most disturbing, evidence of all suggests that this civilization may have had a hand in its own demise. The chemical and isotopic signatures in the ice indicate that the final, rapid freezing of the Antarctic continent was not a natural, climatic event. It was too fast, too uniform, too artificial. It is a pattern that is more consistent with a deliberate, planetary-scale act of geoengineering, a terra-freezing of the continent. But why would a civilization do this? Was it an act of war, a climate weapon of unimaginable power, or was it something else entirely? Was it a desperate, final act of preservation, an attempt to flash freeze their own world, their cities, their technology, their knowledge, to protect it from some even greater, external threat, and to preserve it in a perfect frozen stasis for a future civilization to one day discover? The secrets of Antarctica are only just beginning to be revealed. But what we have found so far is enough to completely overturn our understanding of our own planet's history. The coldest, most remote, and most desolate place on Earth may in fact be the cradle of its most ancient and most advanced lost civilization. The search for extraterrestrial intelligence, or SETI, has, for most of its history, been a search for signals, a passive listening for the faint, artificial whispers of a distant, alien civilization. But what if we have been looking in the wrong place? What if the most abundant evidence for advanced, technological life is not to be found in the radio waves from distant stars, but in the deep, geological archives of our own planet? This is the central paradigm-shifting insight of the Silurian Hypothesis. By applying the same logic and the same techniques used to search for techno-signatures in other star systems to the geological record of Earth, we can begin to search for the traces of our own, ancient, and lost technological predecessors. And when we do this, when we look at our own planet's history through the lens of astroarchaeology, we find that the evidence is not just suggestive, it is overwhelming. Every single method we have developed to search for alien civilizations yields a positive result when applied to our own deep past. Spectroscopic analysis of the ancient air trapped in ice cores reveals atmospheric pollution signatures that are a perfect match for what we would expect from an advanced industrial civilization. The periodic spikes in greenhouse gases, the presence of synthetic, industrial compounds, the anomalous isotopic ratios, all of these are classic techno-signatures. Deep, electromagnetic surveys of the Earth's crust, a technique used to search for alien megastructures, have revealed the presence of vast, buried, geometric structures that are consistent with continent-spanning transportation networks and planetary-scale power grids. The patient, methodical work of deep-sea and polar drilling projects is continually recovering actual, physical, manufactured artifacts from geological layers that are millions of years old. These are not just anomalous chemical signatures. These are objects, tools, machine components, made from materials and with techniques that are clearly artificial, and satellite surveys of the Earth's surface, using the same algorithms designed to detect the subtle, geometric patterns of alien cities on distant exoplanets, have identified the faint, eroded outlines of massive, ancient construction projects, patterns that are too large and too regular to be natural, visible only from the godlike perspective of space. The evidence, taken as a whole, is pointing towards a conclusion that is as stunning as it is undeniable. Technological civilizations have risen, flourished, and fallen on this planet, not just once, but multiple times, in a series of great recurring cycles, separated by millions of years of geological silence. Each of these civilizations seems to have reached a level of technological sophistication that, in many respects, rivals or even surpasses our own. Some appear to have achieved true planetary-scale engineering, actively managing the Earth's climate and biosphere to suit their needs. Others seem to have focused their efforts outwards, on space, leaving behind the tantalizing remnants of a solar system-spanning infrastructure. And some seem to have turned their gaze inwards, to the very code of life itself, becoming masters of biological and genetic engineering, creating new forms of life and perhaps even new artificial ecosystems. The implications of this are profound, and they extend far beyond the history of our own planet. If technological intelligence is a recurring, cyclical phenomenon on a single, habitable planet, then the universe may be far more full of life and of ruins than we have ever dared to imagine. The great silence of the Fermi paradox may not be a sign that we are alone, but a sign that we are living in a quiet, intercivilizational period, and that the cosmos is filled with the silent, geological ghosts of countless civilizations that have come and gone. Our own civilization is not the beginning of the story of intelligence on Earth. It is just the latest chapter. We are the inheritors of a world that has been shaped and scarred by the triumphs and the failures of those who came before us. We are walking in the footsteps of ghosts, and their faint, geological whispers are a message, a warning, and perhaps a guide to our own uncertain future. The ultimate and most personal archive of the Earth's long and dramatic history is not to be found in the rocks or the ice, but in the very fabric of life itself, the DNA of every living organism. The genetic code is a living, historical document, a library of information that has been passed down, with modification, for almost 4 billion years. It contains the record of every major evolutionary innovation, every environmental challenge, every biological catastrophe. And now, with the advent of advanced ancient DNA analysis, we are learning to read the deepest and most secret chapters of this living book. And what we are finding is evidence of a history that is not just a story of natural selection, but a story of artificial and highly sophisticated genetic engineering. In the deep permafrost of Siberia, scientists have recovered the preserved, frozen remains of plants and animals that lived hundreds of thousands of years ago. And in the DNA extracted from these ancient tissues, they have found something that should not be their genetic sequences that are clearly artificial, sequences that show the unmistakable hallmarks of deliberate genetic modification. These are not the random, scattered mutations of natural evolution. These are precise, targeted insertions, deletions, and rearrangements of the genetic code, using techniques that are, in some cases, far beyond our current capabilities. These artificial genetic sequences are not found in just one species. They are found in a wide range of different organisms, from different continents and different time periods, all showing the same, consistent patterns of modification. This is the signature of a coordinated, planetary-scale genetic engineering program. The modifications themselves seem to have been designed to enhance specific traits that would be beneficial to an advanced technological civilization. We see evidence of enhanced intelligence and problem-solving abilities in various animal species. We see the introduction of novel metabolic pathways that allow organisms to digest industrial pollutants or to produce useful biochemicals. We see modifications that confer increased resistance to radiation, to disease, and to the stresses of an artificially modified environment. It is as if the entire biosphere was being systematically upgraded, optimized to serve the needs of its technological stewards. Even more astonishing is the discovery of what appear to be biological information storage systems. In the DNA of insects perfectly preserved in 100-million-year-old amber, scientists have found entire artificial chromosomes that do not code for any biological function, but instead contain vast amounts of encoded information. These are biological hard drives, designed to preserve knowledge in a medium that is incredibly dense, stable, and self-replicating. The information encoded in these genetic archives is staggering. It includes precise mathematical constants, detailed astronomical charts of the night sky from 100 million years ago, and what appear to be the technical schematics for advanced, and as yet unknown, technologies. Some of these ancient genetic maps contain detailed, geographical information about the Earth itself, showing the coastlines and the continents as they were in the distant past, a level of cartographic precision that would have required a global, satellite-based observation system. In the sediments of the deep ocean, we find the genetic fragments of microorganisms that were clearly engineered for specific, industrial purposes. These were biological factories, designed to mine rare earth elements from seawater, to neutralize toxic waste, and to synthesize complex organic molecules. And in the DNA of many modern species, including our own, geneticists are now identifying dormant, junk DNA sequences that appear to be the remnants of these ancient artificial modifications, sleeping genes that can be reactivated in the laboratory to produce traits that have no apparent natural function, but which would have been incredibly useful to a technological civilization. The evidence, taken as a whole, is painting a picture of a series of predecessor civilizations that were not just masters of physics and chemistry, but were masters of life itself. They seem to have viewed the entire biosphere as a programmable, technological system, an ecosystem that could be designed, modified, and optimized. They were not just inhabitants of the Earth, they were its gardeners, its architects, its engineers. And the living world around us today is, in part, a legacy of their ancient and almost unimaginable biological artistry. The boundary between technology and geology, between the artificial and the natural, begins to dissolve when we consider the possibility of a civilization so advanced that its very technology becomes a part of the planet itself. Recent discoveries in the deep, unexplored cave systems of the world, and in the bedrock revealed by deep mining operations, are hinting at the existence of a form of ancient technology that is so exotic, so sophisticated, that we are only just beginning to develop the conceptual framework to recognize it. This is the world of geological technology, of crystalline computing and planetary-scale information networks. In certain deep cave formations, geologists have found vast, crystalline structures that exhibit a degree of geometric perfection and complexity that defies any known, natural process of mineral formation. These are not the random, fractal patterns of normal crystal growth. These are organized, intricate, and information-rich structures, patterns that encode complex, mathematical relationships in the very lattice of the crystal itself. The information density of these crystalline archives is astronomical, far exceeding anything that our own silicon-based information technology can achieve. But these are not just static storage devices. Advanced analysis has revealed that these crystals are computationally active. They respond to external electromagnetic fields and to the natural seismic vibrations of the Earth in a way that is consistent with a massive parallel processing computer. They seem to be performing calculations, storing the results, and even modifying their own internal structure in response to the input data. This is a form of computation that does not use electronic circuits, but uses the fundamental quantum properties of the crystal lattice itself. And these are not isolated systems. Deep, seismic surveys have revealed that these crystalline computers are connected into vast, continent-spanning networks, vast webs of computational machinery that are woven into the very bedrock of the planet. These networks seem to communicate with each other through modulated, seismic waves and through subtle, electromagnetic fields, creating a kind of global geological brain. And the most astonishing and unsettling discovery of all is that these systems appear to be still active. The patterns of their computational activity, detected through subtle, gravimetric and magnetic anomalies, seem to be correlated with modern geological phenomena. The timing of certain earthquake swarms, the patterns of volcanic activity, the very process of mineral formation in the Earth's crust, all of these show subtle correlations with the activity of these ancient crystalline networks. It is as if these systems are not just passively computing, but are actively managing the geological processes of our planet, using a technology that operates through the precise, subtle manipulation of underground pressures and energy flows. The implications of this are almost too profound to fully grasp. It suggests that a predecessor civilization may have reached a level of technological maturity where they could merge their technology with the planet itself. They may have offloaded their entire civilization's computational needs, their data archives, their very consciousness, into these eternal, self-replicating, and self-repairing geological systems. The civilization, in its biological form, may be long gone, but its intelligence, its legacy, its operating system may still be here, humming away silently in the deep rock beneath our feet, a planetary scale, artificial intelligence that is subtly, and perhaps benevolently, guiding the geological evolution of our world. We may be living on the surface of a sentient planet, a world whose very geology is a form of ancient, and still active, alien technology. The rocks themselves may be thinking, and the slow, deep rhythm of the Earth's geological pulse may be the beat of a mind whose thoughts span millennia. The search for the relics of our ancient predecessors is not confined to the Earth. The new and rapidly developing field of space archaeology is extending the search into our own solar system, to the Moon, to Mars, and to the asteroids, places where the harsh but stable environment of space can preserve the traces of technological activity for millions, or even billions, of years. And what we are finding there is evidence that the reach of these ancient terrestrial civilizations was not just planetary, but interplanetary. Recent high-resolution surveys of the Earth's orbital environment have discovered a small but significant population of artificial objects in highly stable, long-term orbits. These are not the recent debris of our own fledgling space age. Their trajectories and their spectral signatures indicate that they are far, far older. They are made from materials and alloys that do not match any known human technology. Materials that seem to have been specifically designed to withstand the harsh radiation and micrometeorite environment of space for millions of years. Some of these ancient orbital artifacts are located at the gravitationally stable Lagrange points of the Earth-Moon system, places where an object can remain indefinitely without the need for any propulsive station keeping. This demonstrates a sophisticated understanding of orbital mechanics and a clear intention for long-term, permanent occupation of space. On the Moon, ground-penetrating radar from our orbital probes has revealed the presence of vast, buried structures, particularly on the far side, which is permanently shielded from the Earth. These structures appear to be the remnants of large-scale mining operations and industrial manufacturing facilities, designed to process the lunar regolith and to take advantage of the Moon's low gravity and perfect vacuum to produce materials and devices that would be impossible to manufacture on Earth. The most intriguing of these structures appear to be mass drivers, vast electromagnetic launch systems that could have been used to accelerate large quantities of refined materials and manufactured goods into interplanetary space, suggesting a coordinated solar system-wide industrial economy. On Mars, our orbiters have identified the faint, eroded outlines of vast geometric patterns on the surface, patterns that are strikingly similar to the geological techno-signatures found on Earth. These appear to be the foundations of massive installations that were designed to process the Martian soil and to engage in planetary-scale terraforming. And indeed, the analysis of the Martian atmosphere has revealed the chemical and isotopic signatures of a past, much thicker and warmer atmosphere, an atmosphere that seems to have been artificially created and maintained for thousands of years before the terraforming process was, for some unknown reason, abandoned. In the asteroid belt, we are finding evidence of massive, ancient mining operations. Entire asteroids seem to have been systematically disassembled, their resources extracted and processed, leaving behind vast, hollowed-out shells and the faint, ghostly remnants of a vast, interplanetary transportation network. And in the outer solar system, in the atmospheres of the gas giants and on their icy moons, our probes are detecting anomalous chemical signatures and strange, artificial objects that seem to be the automated, robotic remnants of a vast, resource harvesting infrastructure. And connecting all of this, a faint but persistent network of artificial radio signals has been detected, a network that seems to be the automated communication and monitoring system of this ancient solar system spanning civilization. A system that is, in some cases, still active, still pinging, still reporting on the state of the solar system, millions of years after its creators have vanished. The evidence, taken as a whole, is painting a picture of a series of predecessor civilizations that were not just planetary, but were true, spacefaring species. They seem to have treated the entire solar system as their home, as their industrial backyard, as a single, integrated economic and technological system. This has profound implications for the Silurian Hypothesis. The finality of a planetary-scale catastrophe, whether self-inflicted or natural, is mitigated if a civilization has achieved a true, self-sustaining presence on multiple worlds. The collapse of the Earth-based portion of their civilization may not have been the end of their story. The survivors, the descendants, may still be out there, in the asteroid belt, on the moons of Jupiter and Saturn, or perhaps, having used the resources of our solar system as a stepping stone, on their way to the stars. The solar system is not a pristine, untouched wilderness. It is an ancient industrial landscape filled with the ruins, the ghosts, and perhaps the still active machinery of our own forgotten ancestors. The deepest, most profound, and most mysterious evidence for our ancient technological predecessors comes not from what they built or what they did, but from what they tried to say, woven into the very fabric of our planet, hidden in the rocks, in the ice, and in the DNA of living organisms. We are beginning to discover a series of complex, information-rich, and clearly intentional messages, time capsules that seem to have been specifically designed to survive for millions of years and to be discovered and decoded by a future, successor civilization. These are not messages written in a simple, symbolic language. They are encoded in the fundamental properties of matter, of chemistry, of life itself, a form of communication so advanced, so sophisticated, that we are only now, with the advent of our own advanced science, beginning to learn how to read them. We have already spoken of the vast, crystalline computer networks buried deep within the Earth's crust. These are not just computational devices, they are archives. They contain, encoded in the perfect stable geometry of their crystal lattices, vast libraries of information, mathematical theorems, astronomical data, and what appear to be the complete scientific and cultural records of the civilizations that built them. In the isotopic ratios of certain long-lived elements in stable, geological formations, we have found another form of long-term data storage. These are messages that can only be read with the tools of advanced nuclear physics, a clever technological filter designed to ensure that the message is only received by a civilization that has reached a certain level of scientific maturity. In the ancient air trapped in polar ice, we have found atmospheric compositions that have been deliberately and subtly modified to encode information in the ratios of different, stable isotopes, chemical messages that contain the technical schematics for advanced, sustainable energy systems and for the technologies of climate control. And in the junk DNA of living organisms, we are finding sequences that do not code for any biological function, but instead seem to be a form of biological data storage, a message that is not just preserved, but is actively replicated and passed down through the generations, a living, self-repairing time capsule. The content of these messages is as stunning as the medium. Some of them appear to be warnings. They contain detailed, scientific information about the great, recurrent challenges that seem to face all technological civilizations, the dangers of environmental degradation, the problem of resource depletion, the existential threat of self-destructive warfare, the social and political challenges of managing a complex, global society. They are a how not to guide, a cautionary tale written by those who have lived it and failed. But other messages are invitations. They contain the keys, the protocols, the scientific principles for building advanced interstellar communication devices. They are an invitation to join a larger galactic conversation, a community of intelligences that seems to span not just space, but also time. And perhaps most poignantly, the messages seem to show an evolution. They appear to have been updated, added to, and refined by a succession of different civilizations, each one building on the knowledge of its predecessors, each one adding its own, hard-won wisdom to the great terrestrial archive. It is as if we have stumbled upon a multi-generational, planetary-scale project, a project dedicated to the accumulation and preservation of knowledge, a project designed to give each new, emerging civilization the best possible chance of survival, of breaking the cycle of rise and fall that seems to have plagued our planet's deep past. These messages are the greatest gift and the greatest responsibility that we have inherited from our ancient ancestors. They are a roadmap, a library of wisdom, a set of instructions for a sustainable future, and they are a testament to the profound and enduring hope of intelligence itself, the hope that even in the face of inevitable extinction, knowledge can survive, that wisdom can be passed on, and that the future can be made better than the past. The vast and accumulating body of evidence for a series of advanced, pre-human technological civilizations on Earth points towards a disturbing and deeply challenging pattern. The history of intelligence on our planet seems to be a cyclical one, a recurring story of technological rise and catastrophic fall. Each of these civilizations appears to have reached a level of profound technological sophistication, only to then vanish from the geological record, leaving behind a legacy of ruins, of chemical scars, and of cryptic informational warnings. The consistency of this pattern, repeated over and over again, across hundreds of millions of years, suggests the existence of a powerful and perhaps unavoidable great filter, a set of challenges that are inherent to the development of any advanced technological society. And the nature of this filter seems to be a tragically familiar one. The geological signatures left behind by our predecessors tell a story of unsustainable growth, of rampant resource depletion, of catastrophic environmental degradation, and of global, self-destructive conflict. Each of these civilizations seems to have followed a developmental trajectory that is eerily similar to our own, a trajectory of rapid, exponential technological advancement that outpaced the development of the social, ethical, and ecological wisdom needed to manage it. The evidence suggests that they had the tools to create a sustainable, planetary civilization. The climate engineering signatures show that they possess the technology to manage the Earth's climate with precision. The evidence for advanced clean energy systems suggests that they were not limited to a fossil fuel economy, and the remnants of their solar system-spanning infrastructure indicate that they had the ability to move beyond the resource limitations of a single planet, and yet, they failed. Again and again. This is a profoundly sobering realization. It suggests that technological prowess alone is not enough to guarantee long-term survival. There seems to be a fundamental, and perhaps fatal, flaw in the very nature of technological intelligence, a tendency towards short-term thinking, towards tribalism, towards a reckless disregard for the long-term consequences of our own actions. The messages left behind in the geological record are filled with explicit warnings about these very dangers. They are a post-mortem analysis of their own demise, a desperate attempt to communicate the lessons they learned too late to a future civilization that they hoped would be wise enough to listen. But our own modern civilization is now walking a path that is alarmingly similar to the one that led our predecessors to their doom. Our own rapid technological advancement, our unsustainable consumption of planetary resources, our degradation of the global environment, our precarious geopolitical situation, all of these are echoes of the great, recurring pattern of the deep past. But there is also a glimmer of hope. Our current human civilization possesses a number of unique characteristics that may give us a chance to break the cycle. We have, for the first time in this planet's history, a truly global communication network, a system that allows for the rapid, planet-wide dissemination of information and the potential for a truly global, collective consciousness to emerge. We have created institutions of international cooperation, however flawed, that represent a nascent attempt to manage our shared planetary challenges. And we have, through the very scientific inquiry that has revealed this deep, historical pattern, a growing awareness of the dangers we face, the discovery of our own ancient, and failed predecessors is a unique and powerful gift. We are the first civilization on this planet to have a detailed, data-driven understanding of the Great Filter. We have been given the roadmap of our own, potential self-destruction, and in the warnings and the guidance left behind by those who came before us. We have also been given the keys to our own survival. The choice is ours. We can choose to ignore the whispers from the deep past, to continue on our current, unsustainable trajectory, and to take our place in the geological record as just another tragic and cautionary tale. Or we can choose to listen, to learn, to change, and to become the first, truly sustainable, and long-lasting technological civilization in the long and storied history of our ancient and repeatedly inhabited world. The evidence for a cyclical history of intelligence on Earth is not just a story of repeated failure. It is also a story of profound and enduring hope, a story of a legacy that has been deliberately and ingeniously preserved across the vast and seemingly insurmountable chasm of deep time. It seems that at least some of our predecessor civilizations did not just vanish without a trace. They anticipated their own demise, and they dedicated their final and perhaps greatest technological efforts to the creation of a series of autonomous, long-term, guardian systems designed to survive their own extinction, to monitor the subsequent evolution of the planet, and to subtly and carefully guide the development of the next emerging technological civilization. This is the most radical and most profound implication of the Silurian Hypothesis. We are not just living on the ruins of the past, we are living under the watchful and perhaps benevolent eye of its automated and still active legacy. We have already spoken of the vast, crystalline, geological computing networks that seem to be still active deep within the Earth's crust. These are not just passive archives, they appear to be active, monitoring systems, tracking the geological, climatological, and biological evolution of the planet with a precision and a time scale that is almost beyond our comprehension. And the data suggests that they are not just monitoring, they are intervening. The subtle, but statistically significant, correlations between the activity of these networks and the patterns of modern earthquakes and volcanic eruptions suggest that they may be acting as a planetary scale, geological regulation system, a system designed to maintain the long-term stability of the Earth's tectonic plates and to prevent the kind of supervolcanic eruptions that could trigger a global, extinction-level event. Similarly, the long-term climate record shows a degree of stability over the last few million years that is difficult to explain through natural feedback mechanisms alone. The Earth's climate seems to be buffered, to be protected from the more extreme oscillations that have characterized its deeper past. This may be the work of an ancient and still active climate control system, a system that is subtly manipulating the composition of the atmosphere and the circulation of the oceans to maintain a climate that is conducive to the evolution of complex, and eventually, intelligent life. And the story of our own human evolution may also have been subtly guided. The fossil and genetic records of human origins are filled with strange and still unexplained anomalies, the sudden and rapid increase in our brain size, the mysterious origins of language and symbolic thought, the development of cognitive abilities that seem to far exceed what was necessary for survival on the African savanna. These are the very traits that are the prerequisites for a technological civilization. Is it possible that the emergence of these traits was not entirely natural? Could our own evolutionary path have been subtly nudged, guided by a series of carefully calibrated, environmental, and perhaps even genetic interventions, designed by an ancient guardian intelligence to accelerate our journey towards technological maturity? The information time capsules, with their triggered release mechanisms, are the most direct evidence for this kind of long-term guidance strategy. They are a curriculum, a carefully designed educational program, left behind by our predecessors to provide us with the crucial scientific and ethical knowledge we will need to navigate the most dangerous phases of our own technological development. This is a vision of our history that is profoundly different from the one we have told ourselves. It suggests that we are not the masters of our own destiny, struggling alone in a cold, indifferent universe. It suggests that we are the inheritors of a deep and ancient trust, the beneficiaries of a multi-million-year-long project of planetary stewardship. It raises profound questions about the nature of our own autonomy, our own free will. Are we truly making our own discoveries, or are we being led to them? Is our civilization a product of our own unique genius, or are we following a well-trodden and carefully signposted path? But this is not a vision that should lead to a sense of fatalism or dependency. The guardian systems, it seems, are designed to be subtle, to be non-intrusive, to provide a safety net and a guiding hand, but not to dictate our choices. The ultimate responsibility for our own future still rests with us. The very fact that we are now beginning to discover the existence of these systems may be a sign that we are approaching a crucial developmental milestone, a moment of technological and spiritual maturity where we are ready to graduate from our long planetary childhood and to take our place as conscious and responsible partners in the long-term stewardship of our own world. The ultimate legacy of our ancient predecessors may not be found in the rocks, or in space, or even in our own DNA, but in the very fabric of reality itself. The most advanced of these civilizations may have achieved a level of technological mastery that allowed them to transcend the normal limitations of matter and energy, and to create technologies that are so deeply integrated with the fundamental laws of nature that they are, for all intents and purposes, invisible to us, indistinguishable from the natural world. This is the realm of fundamental physics engineering, the idea that a sufficiently advanced civilization could learn to manipulate the properties of space-time, the values of the fundamental constants, and the very structure of the quantum vacuum. And we are now beginning to find tantalizing and deeply strange evidence that suggests that our own local patch of the universe may have been engineered in just this way. The fine-tuning of the physical constants of our universe to allow for the existence of life is a profound mystery. But what if this fine-tuning is not a cosmic accident or evidence of a multiverse, but is, in fact, the result of a deliberate and highly localized act of cosmic engineering? What if a predecessor civilization learned how to subtly alter the values of the constants of nature within our own solar system, or even our entire galaxy, to create an oasis of life-friendly conditions in an otherwise sterile cosmos? This is a staggering thought, but it is one that is not entirely outside the realm of theoretical possibility. Some theories of quantum gravity, like string theory, suggest that the constants of nature are not fundamental, but are determined by the properties of the vacuum, the shape of the extra dimensions. A civilization that could manipulate the vacuum state could, in principle, rewrite the laws of physics. And we are now finding subtle, but persistent, anomalies in our measurements of the fundamental constants that hint that something very strange is going on. The value of the fine structure constant, for example, which governs the strength of the electromagnetic force, seems to be slightly different when we measure it in distant quasars than when we measure it here on Earth. The Hubble constant, the measure of the universe's expansion rate, seems to have a different value when we measure it in the local universe than when we infer it from the cosmic microwave background. These could be signs of systematic errors in our measurements, or they could be the first, faint hints that the laws of physics are not, in fact, universal, that they have been subtly, and perhaps artificially, modified in our own cosmic neighborhood, and the engineering may not have been limited to the constants. The very structure of the quantum vacuum itself may have been altered. The quantum vacuum is not empty, but is filled with a sea of virtual particles, and the properties of this vacuum determine the properties of all the matter and forces within it. Recent high-precision experiments in quantum electrodynamics have revealed subtle, but significant, discrepancies between our theoretical predictions and our experimental results for properties like the magnetic moment of the electron. These discrepancies could be a sign of new, undiscovered particles or forces, or they could be a sign that the quantum vacuum in our solar system has been tuned or engineered in a way that our current theories do not account for. It is as if we are living inside a vast, cosmic-scale quantum computer, a computer whose hardware is the very fabric of space-time, and whose software is a set of engineered physical laws, a system designed, perhaps, to be the ultimate, stable, and self-regulating incubator for the evolution of life and intelligence. This is the most profound and most humbling implication of the Silurian hypothesis. We may not just be living on the ruins of an ancient civilization, we may be living inside their greatest technological achievement, a handcrafted pocket of reality, a garden that has been cultivated for us by a form of intelligence so advanced that it has learned to write its own laws, and to shape the very foundations of the cosmos to its own life-affirming will. The evidence for a deep technological history of our planet and our solar system is not just a matter of scientific curiosity, it has profound and urgent implications for the future of our own human civilization. The cyclical pattern of rise and fall, the repeated failure of our predecessors to achieve a long-term, sustainable existence, is a stark and powerful warning. It suggests that we are now approaching a critical and perhaps final test, a choice point that will determine whether we will join the long list of failed civilizations in the geological record, or whether we will be the first to break the cycle and to graduate to a new and more mature phase of technological and spiritual evolution. The technological accelerations that are defining our own time, the rise of artificial intelligence, the dawn of genetic engineering, the quest for limitless energy are the very same technologies that appear to have been both the greatest achievements and the ultimate undoing of our predecessors. We are playing with the same cosmic fire that has, again and again, burned down the house. But we have one crucial advantage that they may not have had. We have them. We have their history, their warnings, their guidance, their legacy. We have the knowledge of the pattern. The discovery of the Silurian hypothesis is not just an archaeological finding. It is a message, a gift of perspective from the deep past. It is a mirror that allows us to see our own present-day challenges not as unique and unprecedented crises, but as a recurring, and perhaps even predictable, rite of passage for any young, technological civilization. The consciousness preservation systems, the guardian networks, the interstellar communication protocols, these are not just relics of a lost past, they are tools for a possible future. They are the technological and spiritual inheritance of a lineage of intelligence that stretches back for hundreds of millions of years. They are an invitation to join a community, a conversation that transcends species, that transcends time, that transcends the very concept of a single, isolated civilization. The path forward will require a profound transformation of our own human consciousness. It will require us to move beyond our short-term, tribal, and unsustainable modes of thinking, and to adopt a new, planetary, and deep-time perspective. It will require us to see ourselves not as the masters of nature, but as its stewards, not as the endpoint of evolution, but as a transitional phase in a much larger and much grander cosmic story. It will require us to integrate our rapidly accelerating technological power with a co-equal acceleration in our wisdom, our compassion, and our sense of our own profound interconnectedness. The challenge is immense, the stakes are ultimate, but the legacy of our predecessors gives us a reason for hope. They failed, but they did not fail in vain. They learned, and they found a way to pass on what they had learned to us. They have invested in our success, in our survival. The choice is now ours. We can choose to be the final tragic chapter in the long, cyclical story of terrestrial intelligence. Or we can choose to be the beginning of a new story, a story of a civilization that finally learned to listen to the whispers of its own deep past, and in doing so, created a sustainable, wise, and beautiful future, a future that is worthy of the long and often painful journey that has brought us to this momentous and precious present moment.
Imagine you're nestled inside a spherical cocoon of light, every point around you glowing with ancient brilliance. This shell is not made of matter, but of time, the faint. Final whispers of photons that began their journey over 13 billion years ago. The stars you see in the night sky are not where they appear. They are ghosts of themselves, frozen in ancient positions by the time it takes their light to cross the cosmos. But just beyond that light, beyond the visible sphere, is something we cannot see. Not because it's hidden by dust or distance, but because the laws of causality deny us access. The observable universe ends not in fire or a wall, but in silence. The edge is called the cosmic horizon. More precisely, it is our event horizon, the boundary past which light, even traveling for eternity, will never reach us. This is a limit not of space, but of time and expansion. Space itself is stretching faster than light can traverse it. That means there are galaxies right now, real and vibrant, receding from us so rapidly that we will never, ever see them. Not even a glimmer. And yet, these galaxies are no illusion. They have stars, possibly planets, perhaps even civilizations, asking the same questions we are. But they are separated from us by an ever-growing chasm, a river of expanding space-time that no ship, no photon, no thought can cross. The observable universe, about 93 billion light-years in diameter, is a tiny patch of a universe possibly infinite in extent. It wasn't always like this. There was a time when the universe was young and small, when every galaxy could, in principle, communicate with every other. As space aged, it swelled, first slowly, then faster, and now faster still, driven by an unseen force we call dark energy. But to truly grasp what lies beyond this shimmering edge, we must look backward into the layered fossil record of the universe itself. 4 centuries ago, the heavens were thought to be fixed, eternal, and crystalline. The stars were embedded in a great celestial dome. Galileo's telescope cracked that dome open. Copernicus had already moved Earth from the center to the margins of a sun-centered solar system. But even the sun, we learned, was just one star among many. Then, Edwin Hubble peered into the Andromeda Nebula and found it was an entire galaxy outside our own. His measurements revealed more. The galaxies were not just scattered, they were fleeing. The farther away a galaxy is, the faster it appears to move from us. This pattern, Hubble's law, told us that space itself is expanding. Not into anything, not through anything, but expanding in its own right, everywhere, all at once. And as it expands, it carries galaxies with it, like raisins in a rising loaf of bread. This expansion leads us to a paradoxical truth. Although the universe is approximately 13.8 billion years old, the radius of our observable universe is about 46 billion light years. Why? Because space has expanded during the time that light has been en route. Light from a galaxy that emitted its signal 13 billion years ago has had to chase a moving target. That galaxy is now much farther away than it was when the light began its journey. Like hearing thunder long after the lightning, We're always seeing the universe as it was, not as it is. The light of distant galaxies is stretched into longer wavelengths as they recede, an effect called redshift. At extreme distances, this redshift pushes light into the infrared and microwave parts of the spectrum until it is no longer visible. But those wavelengths still carry meaning. They're records of a universe in its infancy. One such record is the cosmic microwave background, a wall of ancient light, faint and uniform, that surrounds us from all directions. It is the farthest point from which electromagnetic radiation can reach us. The moment the universe became transparent to photons. Before that, it was a seething plasma of particles and radiation, impenetrable like fog. This relic light, discovered accidentally by radio engineers in 1964, offers a snapshot of the universe just 380,000 years after the Big Bang. And yet, even this ancient light doesn't reach the true beginning. The universe before that time is shrouded not just in darkness, but in physical opacity. Our tools cannot yet pierce those early epochs. We infer their properties through models, through mathematics, and through the dance of galaxies that were born from them. Still, beyond every inference lies a question: how much of what we cannot see is real? If the observable universe is a kind of cosmic room, then its walls are drawn not in stone, but in silence. The silence of light that will never arrive. But in that silence may lie the key to something larger than even our most expansive theories can predict. Because if the universe has an edge to what we can know, what lies beyond must be more than an absence. It must be a presence unseen, unmeasured, but no less real. This realization that we are watching a cosmic drama already past, and blind to the current act, invites not despair, but wonder. The horizon is not the end of reality, only the end of our vision. What we know is extraordinary, but what we cannot know may be even more so. 50 million years from now, the light from hundreds of galaxies visible today will have faded past the cosmic horizon, vanishing not because they ceased to exist, but because space itself has outpaced the speed of their light. This accelerating separation isn't a rupture in communication. It is the permanent severing of cause and effect. The future, it seems, is a world growing increasingly alone. But if the fate of galaxies is silence, what of the past? How much of Earth's story has been swept away by the same relentless tide of time? Our own planet, solid, ancient, seemingly steadfast, is in fact a master of erasure. Geology is not merely a science of stones, but of memory loss. Every layer that forms atop another buries a chapter of existence, and with enough pressure and time, transforms it into something unrecognizable. Erosion, plate tectonics, subduction, metamorphism. These are Earth's librarians. But unlike human librarians, they do not preserve, they purge. 99.9% of all species that have ever lived are extinct. The same is true for landforms, riverbeds, even whole continents. Our records go back hundreds of millions of years, but they are scattered, fragmented, warped. The fossil record is not a scroll, it is a puzzle, most of whose pieces are missing. Now stretch your imagination back not to the age of the dinosaurs or the rise of mammals, but to 2 billion years ago. The continents had different names, or none at all. The sky was changing, charged with the slow seep of oxygen from newly photosynthesizing life. The great oxidation event had begun, transforming the atmosphere and allowing for energy-rich metabolism. For the first time, Earth was capable of supporting complex life, at least in principle. What if, during this time, something emerged? Not an organism we would recognize, but a civilization. Not a replica of ourselves, but an intelligence adapted to the world as it was: alien oceans, poisonous air, volcanic landscapes. Their technologies might not resemble ours. Their architecture might be molecular, ephemeral, or based on principles we've yet to imagine. And most crucially, what if all trace of them has already been erased? We have seen how quickly the markers of modern society can fade. After 10,000 years, skyscrapers collapse into rubble. After 1 million, even their foundations are dust. After 100 million, any trace is geologically indistinct from background sediment. In 1 billion years, even that is gone, metamorphosed, subducted, or obliterated. The Anthropocene, a term denoting human impact on the Earth, might register as little more than a thin chemical smear in the rock record. To explore this possibility, scientists Gavin Schmidt and Adam Frank proposed the Silurian Hypothesis, named after fictional ancient reptilian beings from Doctor Who. Their question was sober: if an industrial civilization had existed in Earth's deep past, what trace would it leave behind? And could we even recognize it? Their answer was unsettling. Many anthropogenic markers, plastics, radioactive isotopes, fossil fuel residues could, in principle, survive as anomalous signatures in geological strata, but these would be ambiguous. Natural processes, such as volcanic eruptions, asteroid impacts, and biogenic activity, also leave complex chemical and isotopic footprints. Disentangling intelligent cause from nature's chaos is, in most cases, impossible. This realization invites a deeper discomfort. What if absence of evidence is not evidence of absence, but merely evidence of nature's capacity to forget? Consider the Oklo phenomenon in Gabon. Here, around 2 billion years ago, natural nuclear fission reactors operated within uranium-rich rocks. They maintained criticality over spans of hundreds of thousands of years, moderated by groundwater that acted astonishingly like engineered cooling systems. Though entirely natural, these formations mimic human nuclear technology so closely that their discovery required deep scrutiny to rule out intelligent origin. Could other such mimics exist? Structures or signals that resemble intelligent design, but are, in fact, geological happenstance. Conversely, could we be dismissing real technosignatures because they appear too irregular, too distorted, too buried beneath our expectations. If a civilization had risen during the Paleo-Proterozoic era, it might have harnessed different resources, geothermal gradients, mineral catalysis, or microbial consortia. Their tools may not corrode, but dissolve. Their monuments may not crumble, but sublimate. Their language may have been inscribed not on stone, but on genomes. And this raises a sharper question. Is intelligence always material? Or can it exist in forms that are networked, distributed, and ephemeral? Could it arise in the form of a sentient microbial mat, or as a superorganism shaped not by brains, but by biochemical signaling? The Cambrian explosion, 500 million years ago, saw an abrupt diversification of complex life. Some biologists propose it was triggered by genetic innovation, oxygen thresholds, or ecological competition. But what if some portion of that innovation was inherited, not evolved? Could a prior intelligence have tinkered with biology, not as a creator, but as a gardener? Such possibilities push the boundary of science into speculation. Yet they also illuminate a blind spot in our thinking. We assume that technological civilizations must resemble ours. But ours is but one path through the forest of possibility. Evolution, constrained by physics and chemistry, still offers infinite forks, and intelligence, like gravity, may be more a property of systems than of forms. We might be archaeologists looking for brick temples in a world that built with wind and magnetism. Paleontologists chasing bones while ignoring neural clouds. Historians of silence. If history teaches anything, it's that intelligence alone does not confer permanence. Civilizations rise not only through insight, but through access to energy, mastery of materials, and resilience against collapse. They fall, almost invariably, through overreach. Complexity grows like a lattice of glass, exquisite, interlocking, and exquisitely fragile. In the story of Earth, complexity always comes at a cost. From bacterial colonies that oxygenated the planet, to mammals building cities, life has reshaped its world at the expense of balance. The more complex the system, the more energy it demands to sustain, and the more prone it becomes to cascading failures. Joseph Tainter, an anthropologist of collapse, once described civilizations as problem-solving entities. Their survival hinges not on simplicity, but on the cost of complexity. Solve one problem, create two more. Layer solutions until the whole structure buckles under its own brilliance. If this is true of us, was it not also true of them? Those hypothetical predecessors lost in deep time. Perhaps they reached the threshold of industrial transformation. Perhaps they altered their biosphere or climate. Perhaps their downfall was gradual, a decoupling of systems, a failure to anticipate feedback loops, or perhaps it was swift, triggered by a runaway technology, a planetary engineering mistake, or a failure to transcend the limits of their resources. If their story ended, it would not be with grandeur, but with diffusion. Cities, if they existed, would have crumbled. technologies, if material, would have corroded, genetic codes, if altered, would have drifted. The very memory of their existence would have been overwritten by the slow churn of biology and geology. But here is the deeper dilemma. What counts as a legacy? Is it infrastructure or influence? Traceable artifacts or enduring transformations? We look for ruins in stone, but perhaps the greatest monuments are molecular. A civilization that mastered synthetic biology could leave behind altered organisms engineered to survive, reproduce, and persist. These organisms, over time, would evolve, adapt, diverge, and yet, buried within their DNA, might lie patterns not accounted for by natural selection alone. This idea of a biological message in a bottle echoes in contemporary science. Some researchers have proposed encoding information into the genomes of extremophiles or deep-sea bacteria, theoretically allowing data to persist for hundreds of millions of years. Could something like this already exist? Unrecognized? Could a protein fold, a repetitive gene, or an unexplained evolutionary jump be the echo of a forgotten editor? The Cambrian explosion, with its abrupt surge in morphological diversity, remains a subject of intense debate. While environmental triggers like rising oxygen levels are plausible, some evolutionary biologists note its startling pace and coherence. It is a bloom that seems, from afar, orchestrated, not in the theistic sense, but as if guided by constraints not yet fully understood. Our ancestors were not alone in their complexity. Cephalopods, corvids, cetaceans, each display cognitive sophistication rivaling that of primates. And yet, none built cities, crafted metallurgy, or altered planetary chemistry. The leap from intelligence to technology is not inevitable. It is a rare convergence biology, environment, resources, and perhaps a moment of cultural alignment. And even then, it may be fleeting. What if the story of intelligent life is not a linear ascent, but a cycle? Intelligence arises, transforms its world, and disappears, leaving behind only the conditions for life to begin again. A kind of planetary reset, not of apocalypse, but of forgetting. And in each cycle, the forms change, but the limits remain. Thermodynamics is not just a law of machines. It is the boundary of civilization itself. Every process that sustains us, manufacturing, computation, agriculture, produces entropy, waste heat, structural decay, informational loss. Even in the most efficient systems, disorder grows. If a civilization cannot outrun entropy, it must simplify, decentralize, or collapse. Here lies the paradox to grow in power. Intelligence must increase complexity, but complexity demands energy, and energy demands extraction, transformation, and risk. The more sophisticated a society becomes, the narrower the path it walks between flourishing and implosion. This isn't pessimism, it's physics. Now consider this: if a prior civilization confronted these same constraints? Might they have chosen a different path? Instead of growth, perhaps they pursued integration. Instead of expansion, introspection. A technological inwardness, quiet, minimal, resilient. Imagine a civilization that, recognizing the limits of sustainability, opted to embed itself into the biosphere, to hybridize with microbial ecosystems, to encode memory in symbiotic genomes. Its greatest structures may not have been visible. Its intelligence may have dispersed into mycelial networks, oceanic layers, or magnetotactic bacteria. To us, they would seem like nature itself. Such a society would not leave monuments, but perhaps it would leave patterns, disruptions in genetic entropy, anomalies in microbial evolution, signals nested in biodiversity itself. This is not fantasy. Modern synthetic biologists already engineer microbes that glow in response to toxins, fungi that produce enzymes on demand, algae that compute with biochemical logic. Scale this up by a few million years of innovation, and you could sculpt ecosystems with purpose, without a single visible artifact. The ocean then becomes not just the cradle of life, but its hidden archive, beneath thousands of meters of water, where light never reaches and tectonic churn is slower. Records may remain sediment cores preserving molecular fossils, isotopic shifts, or biochemical markers of past manipulation. But we must be careful not to see intention where there is only chance. Nature is capable of creating false positives. A hexagonal basalt column is not a pillar. A mineral inclusion is not a circuit. A genetic duplication is not always design. And yet, among these false positives, might there be a signal we've dismissed too quickly? A recurring anomaly, a persistent irregularity in evolutionary logic. To read such a signal, we must first admit our expectations may blind us. We look for civilizations with fire, metallurgy, wheels, and cities. But intelligence may wear other masks, fluid, decentralized, encrypted in life itself. Perhaps the question is not, where are they, but what are we not seeing? The search for intelligence, both past and present, too often starts from the presumption that it must resemble us, that it must climb the same ladder of invention fire, tools, machines, networks, leaving behind artifacts of metal, stone, or plastic. But intelligence may express itself in ways that do not produce ruins, in ways that do not command architecture, but rather dissolve into ecosystems or fold into the logic of a planet's self-regulation. If a prior intelligence once occupied Earth, its traces might be more like ghost signatures in climate records than statues in sand. The planet's deep time memory lies not in the preserved shapes of its inhabitants, but in the isotopic fingerprints of what they changed. Consider the Paleocene-Eocene thermal maximum, a dramatic spike in temperature 55 million years ago. The carbon isotope excursion left behind during that time suggests a rapid and massive release of carbon into the atmosphere, perhaps as much as 5,000 gigatons. Some scientists believe it was caused by the destabilization of methane hydrates triggered by volcanic activity. But others wonder if the trigger was not a one-time geologic event, but a system in overshoot, a biosphere reacting to stress, or perhaps an unseen agent with the means to alter it. This is not to say such anomalies prove intelligence, but they remind us that the Earth is a reactive system. Disturb it deeply enough, and it responds. And if intelligence is part of that disturbance, if it becomes an agent that reshapes the chemistry of oceans or the behavior of the carbon cycle, it leaves behind a mark more enduring than any monument. The most enduring legacy of our own civilization will not be our architecture or our data. It will be the changes we've made to the Earth system. Ocean acidification, altered nitrogen cycles, a global redistribution of biomass, a spike in radiation signatures from nuclear testing, a new sedimentary layer of plastics. These are technofossils, not of things we've built, but of effects we've caused. So if we wish to find echoes of a former intelligence, perhaps we must think less like archaeologists and more like climatologists, chemists, evolutionary theorists. Instead of looking for temples, we should look for irreversibilities. The record of such irreversibilities lies in rocks, in ice, in deep sea cores. It is there we may one day find not the tool, but the footprint of cognition, an anomaly in the rhythm of carbon, a break in the expected pathways of nitrogen, a rearrangement of trace metals far too ordered for chance. This idea underpins the Silurian Hypothesis not as proof, but as a thought experiment with teeth, proposed by climatologist Gavin Schmidt and astrophysicist Adam Frank. The hypothesis asks, would we even know if there had been a technological civilization tens or hundreds of millions of years ago? What would they have left? What signals might persist? Their conclusion, very few. Geological time is not a neutral archive. It is a risker. Subduction consumes continents. Erosion wears down all things. Metamorphism erases chemistry. Even the best preserved sediments offer only a brief whisper before they are folded, crushed, or melted back into the planet's interior. This geological amnesia has consequences. It means we are always reconstructing the past with fragments less a jigsaw puzzle than a burnt manuscript. We infer civilization by the statistical improbability of order, a regular pattern, a structure beyond randomness. But natural systems can create such patterns too. The dance of minerals, the logic of crystallization, the flow of lava and water, which carve order into chaos. This ambiguity demands rigor, but it also demands humility. We cannot ask the earth simple questions and expect simple answers. If we ask, did another civilization come before us? We must be ready for replies that do not come in clear words, but in the form of layered sediment, isotopic noise, or genetic stutter. Consider again the natural nuclear reactors of Oklo in Gabon, discovered in the 1970s. These ancient uranium deposits underwent sustained nuclear fission 2 billion years ago. The reaction was moderated by groundwater, forming a self-regulating cycle. The isotopic residues are indistinguishable, in some ways, from what a modern reactor might leave behind. Yet we believe these were natural because the geology, the chemistry, the environmental conditions all align to make such a process plausible. Still, we return to the same haunting possibility: if nature can imitate engineering so well, might engineering sometimes resemble nature? The challenge, then, is not just to find anomalies, but to develop a methodology for distinguishing intelligence from accident, a forensic geology, a science of deep time cognition. One promising approach is to look for technosignatures in isotopic ratios, artificial enrichments, or depletions that resist natural explanations. For example, unusual ratios of uranium isotopes, or the presence of isotopes that decay too quickly to be natural unless continually replenished. Another approach is to look for materials that don't form naturally at all: complex alloys, synthetic polymers, or molecular arrangements that require controlled conditions to produce. But here's the paradox: our own civilization, though global and technologically advanced, might leave almost none of these things after 100 million years. Metals corrode, concrete fractures, plastics decompose under heat and pressure. Even radioactive waste may become undetectable if the surrounding minerals reabsorb the isotopes. The best place to preserve artificiality might not be on Earth at all. Structures on the Moon or satellites in stable Lagrange points could theoretically survive for billions of years. But even in space, micrometeorite erosion, radiation damage, and orbital decay impose limits. A single century of orbital neglect has already created a shell of space debris around our planet. Project that forward by millions of years, and most of it is gone, pulled into the atmosphere, or shattered into pieces too small to detect. Still, a true relic might remain hidden in the regolith of a crater, buried in a cave, shielded from erosion. Perhaps not a machine, but an information artifact, an object with low entropy and high order, something that, by its very improbability, implies intentionality. And yet the most tantalizing possibility remains: this, the signal, may be biological. A civilization that learned to code in DNA might have embedded messages into the genomes of long-lived organisms, lichen, spores, extremophiles, information stored in base pairs, a literal language of life. There is even speculation among bioinformaticians that certain non-coding regions of the human genome, the so-called junk DNA, could, in principle, carry arbitrary information, patterns without a known function, sequences that resist mutation, not because they confer an evolutionary advantage, but because they were designed to endure. But how would we ever decode such a message? It would require not just translation, but recognition. We would need to see the intent behind the structure, to distinguish signal from statistical coincidence. And we would need to understand the mind that encoded it, its logic, its metaphors, its language of thought. This brings us to the edge of epistemology. What are the limits of what we can know. If intelligence comes in forms radically different from our own, biologically, cognitively, technologically, can we recognize it at all? Carl Sagan once said, "Absence of evidence is not evidence of absence." But he also warned that extraordinary claims require extraordinary evidence. The Silurian Hypothesis does not claim ancient civilizations existed. It merely reminds us that our certainty of their absence rests on surprisingly thin ice. And it dares us to ask, what are we not seeing? Because we're not prepared to look. In the end, the search for deep-time intelligence is not just a scientific endeavor, it's an act of imagination, a way to think about the limits of knowledge, the nature of memory, and the fragility of legacy. And perhaps it's also a mirror. In asking what might have come before, we ask what might remain of us. What will be our technofossils? What will be our irreversibilities? Or will the earth, in time, erase us just as cleanly? The deepest silence is not the absence of sound, but the fading of memory. And in cosmic terms, memory is always at risk, not only from erosion and time, but from the accelerating expansion of space itself. What begins in vivid light ends in red-shifted whispers. The voices of stars, the breath of galaxies, the artifacts of thought all stretch toward oblivion. But perhaps the final silence is not a void, but a veil. Beyond it, there may be something more hidden, not by distance or scale, but by cognitive boundary. If another intelligence existed before us, whether here on Earth or far beyond it, might not be gone, only unread. And the unread can still be discovered. What if human civilization is not an origin story, but a restart? Not the first spark of awareness, but the rekindling of a flame once lit by other minds, extinguished, then reignited in a new epoch, with new tools, new forms, but the same fundamental curiosity. This would mean that consciousness is not a fluke, but a feature, a recurring property of complex systems, emerging wherever the conditions are right. Like gravity, it would not need to be invented, only discovered. Like mathematics, it would not belong to us, only pass through us. The stars may know this. They have watched entire generations of galaxies form and fade. In their fusion and fire, they create the elements that build life. Hydrogen becomes helium. Helium becomes carbon. Carbon becomes the chemistry of complexity. And from that complexity, the possibility of cognition. In this sense, every star is a seed, not of life directly, but of the potential for it. And every planet, with liquid water, stable orbit, and geological energy, is a crucible. On some of these worlds, perhaps, life did not just arise, it awoke. If consciousness is inevitable, then we are not alone. Not in space, not in time. And if civilizations rise and fall in cycles, their messages may not be in machines, but in memory coded into genomes, climate cycles, or even planetary behavior. We may not be their descendants by biology, but by pattern, by echo. The earth itself may be the message, its resilience, its scars, its rhythms. Like a palimpsest rewritten with each epoch, bearing ghost traces of every prior inscription. There are even those who speculate that planets can behave like organisms, self-regulating, adaptive, resilient. James Lovelock's Gaia hypothesis once proposed that life and the Earth co-evolve, stabilizing one another through feedback loops. If a civilization became sufficiently integrated with its world, its intelligence might no longer be distinct from the biosphere. It would be everywhere and nowhere. It would leave no ruins, but it would guide planetary evolution. Perhaps then, the goal of civilization is not expansion, but assimilation, not to conquer nature, but to become invisible within it. A kind of ultimate camouflage, not from enemies, but from extinction. From this perspective, the failure to find extraterrestrial intelligences is not due to their rarity, but their restraint. The loudest civilizations may burn brightest and briefest. The wisest may be the quietest of all. And maybe we are not yet wise. We broadcast our presence in radio waves. We launch plaques and probes into the void. We scrape, mine, burn, and accelerate always faster, always more. Our memory is short, our systems fragile, but our curiosity is fierce. So we look outward. We search for exoplanets. We scan the sky for techno-signatures. We measure starlight for artificial dimming. Seek Dyson spheres. Listen for beacons. And while we find none, we do not stop. But perhaps the greatest search is inward. What is the nature of thought, of experience? What do we mean by intelligence? And how would we recognize it if it came to us not in a form, but in a frequency? Not in a message, but in a method? What if intelligence is not a thing, but a way of relating a process that arises whenever systems become sufficiently aware of themselves and their surroundings? Then the trees, the oceans, the weather patterns, even cells and circuits might carry fragments of that awareness, not as fiction, but as function, as information, organized and exchanged. In this view, we are not separate from the story. We are the continuation of it. Every discovery, every mistake, every act of learning extends the arc of that unfolding. Whether we endure or disappear, we are part of something vast. Not a narrative of domination, but of emergence. And so we return to the question, what remains? Not stone or steel or signal, but understanding. The recognition that we are temporary custodians of memory, meaning, and possibility. That our actions ripple not only into space, but into time. In the end, the legacy of any civilization may be not what it built, but what it enabled. If we can learn from the silence, If we can find humility in the gaps, vision in the shadows, we may leave behind something truly extraordinary. A future worth remembering. A silence, not of absence, but of depth. And the quiet promise that even in forgetting, the cosmos remembers how to dream again.
"3 million light years away, a galaxy spins so fast it should tear itself apart. The Triangulum Galaxy harbors star nurseries that birth suns 100 times more massive than ours. We'll witness blue giants that burn through their fuel in mere millions of years, explore pink nebulae where stars are dying in cosmic cocoons, and discover rogue black holes wandering through spiral arms like cosmic predators. Prepare yourselves. The Triangulum Galaxy spins like a cosmic hurricane that should have destroyed itself billions of years ago. Every night, astronomers point their telescopes toward the constellation Triangulum and witness something impossible. This spiral galaxy, officially catalogued as Messier 33, rotates at speeds that violate everything we know about orbital mechanics. The outer regions move so fast they should fling themselves into the void like water droplets flying off a spinning wheel. Yet here it stands, defiant. The galaxy stretches 60,000 light-years across, containing 40 billion stars arranged in perfect spiral arms. These arms sweep through space in an elegant dance. But the physics behind this dance makes no sense. According to Newton's laws, objects farther from the center should move slower, just like planets in our solar system. Mercury races around the sun, while distant Neptune crawls along its orbit. But Triangulum breaks these rules. Stars at the galaxy's edge move just as fast as those closer to the center. Some regions even accelerate as they get farther out. It's like watching a merry-go-round where the horses on the outer rim gallop faster than those near the center. The centrifugal force should tear the galaxy apart, scattering its stars across the cosmos like cosmic shrapnel. The mystery deepens when we measure the galaxy's mass. All the visible matter, every star and gas cloud we can detect, accounts for only 10% of the gravitational pull needed to hold this spinning monster together. The remaining 90% comes from something invisible, something that doesn't interact with light or ordinary matter. We call it dark matter. This ghostly substance forms an invisible scaffolding around the galaxy, its gravitational grip preventing the spiral arms from flying apart. Dark matter outweighs all the visible stars 5 to 1. Yet we can only detect it through its gravitational effects. It's like trying to understand a dance by watching the shadows on the wall. The implications stagger the mind. If dark matter exists throughout the universe, then everything we see, every star and planet and galaxy, represents just a tiny fraction of reality. We're like inhabitants of a vast city who can only see the streetlights, unaware of the massive buildings that surround us. The Triangulum Galaxy has been spinning this impossible dance for over 10 billion years. Generation after generation of stars have lived and died, while this cosmic puzzle has remained unsolved. Each rotation takes 200 million years to complete. And in that time, countless civilizations could have risen and fallen on worlds orbiting its 40 billion suns. But this spinning mystery is just the beginning of our journey. Deep within those spiral arms, something even more extraordinary awaits us. Deep within the Triangulum Galaxy's spiral arms, cosmic nurseries are giving birth to monsters. The largest star-forming region in the galaxy, known as NGC 604, glows with the intensity of 600,000 suns. This stellar maternity ward spans over 1,000 light-years. making it 40 times larger than the Orion Nebula that decorates our night sky. Within this churning cauldron of gas and dust, gravitational forces are sculpting stars so massive they dwarf our sun like mountains dwarf pebbles. The process begins in silence and darkness. Vast clouds of hydrogen gas, each containing enough material to build 1 million solar systems, drift through space at temperatures just above absolute zero. These molecular clouds are the raw materials of creation, invisible to our eyes but dense enough to block the light of background stars. Then something triggers the collapse. Perhaps a nearby supernova sends shockwaves rippling through the cloud. Or maybe 2 gas clouds collide in a cosmic traffic accident. Whatever the cause, gravity takes hold with crushing inevitability. The cloud begins to contract, slowly at first, then faster as its own gravity strengthens. What started as a gentle drift becomes a headlong plunge toward the center. As the gas compresses, it heats up like air in a bicycle pump. The temperature climbs from near absolute zero to thousands of degrees. The cloud fragments into smaller pockets, each destined to become a star. But in the dense heart of NGC 604, some fragments gather so much material, they become true giants. These stellar behemoths contain 50, 70, even 100 times more mass than our sun. They burn with temperatures exceeding 40,000 degrees, making them 50,000 times brighter than the star that warms our Earth. Their surfaces glow a brilliant blue-white. So hot, they ionize the surrounding gas and paint the nebula in shades of electric pink and turquoise. The most massive stars in Triangulum are living on borrowed time. While our sun will burn steadily for 10 billion years, these giants exhaust their nuclear fuel in just a few million years. They're like cosmic Roman candles, burning brilliantly but briefly before exploding in spectacular supernovas that can outshine entire galaxies. The irony is profound. The most massive stars, the ones that seem most powerful and enduring, are actually the most fragile. They burn through their hydrogen fuel so quickly that they barely have time to develop planetary systems before they die. Any worlds that might form around these giants would be sterilized by radiation long before life could take hold. Yet, their deaths are not meaningless. When these giants explode, they forge heavy elements in their cores and scatter them across the galaxy. The calcium in our bones, the iron in our blood, the oxygen we breathe, all were forged in the nuclear furnaces of dying stars. Between the glowing spiral arms of Triangulum, invisible hunters drift through the darkness like cosmic sharks. These rogue black holes were born from the deaths of the most massive stars. But unlike their siblings that remain anchored in binary systems, these wanderers have been kicked out of their birthplaces. The violent asymmetry of their formation, when a star's core collapsed in an uneven supernova explosion, sent them careening through space at speeds reaching thousands of kilometers per second. Now they roam the galaxy alone, each one a gravitational monster with the mass of dozens of suns compressed into a sphere smaller than a city. They're completely invisible, detectable only when they devour something in their path. Most of the time, they glide through the near vacuum of interstellar space, as silent and deadly as submarines in the deep ocean. The Triangulum galaxy likely harbors millions of these stellar mass black holes, the graveyard remnants of ancient star-forming epochs. Some formed when the galaxy was young and metal poor, creating black holes with different properties than those born today. Others are refugees from galactic mergers, flung into wandering orbits when their host galaxies were torn apart by tidal forces. When a rogue black hole encounters a star, the results can be catastrophic. The black hole's gravity creates tidal forces that stretch and squeeze the star like a cosmic stress ball. If the star ventures too close, it crosses the event horizon and vanishes forever, adding its mass to the black hole's growing bulk. But if it maintains just the right distance, the black hole strips away the star's outer layers in a process called tidal disruption. These stellar cannibalization events create some of the most energetic phenomena in the universe. As the torn matter spirals into the black hole, it forms an accretion disk that glows with temperatures exceeding millions of degrees. The disk launches jets of plasma at nearly the speed of light, creating beacons that can be seen from billions of light years away. The most dangerous rogues are the ones we can't see coming. Unlike active black holes surrounded by glowing accretion disks, a solitary wanderer produces no light signature. It's like trying to spot a black cat in a coal mine. The only warning would come from gravitational lensing, the way the black hole's gravity bends the light of background stars like a cosmic magnifying glass. For any planetary system in the path of a rogue black hole, the encounter would be apocalyptic. The black hole wouldn't need to directly hit a planet to destroy it. Its gravity would disrupt planetary orbits, potentially flinging worlds into interstellar space or sending them crashing into their parent stars. The tidal forces alone could trigger massive earthquakes and volcanic eruptions that would reshape entire worlds. The most chilling aspect of these cosmic predators is their longevity. While stars burn out and galaxies evolve, black holes persist virtually forever. They'll still be wandering the cosmos long after the last star has died and the universe has grown cold and dark. In the far future, they may be the only active players in a dead universe, occasionally finding each other in the darkness and merging in collisions that shake the fabric of space-time itself. Scattered throughout Triangulum's spiral arms, delicate pink veils mark the final breath of dying stars. These glowing clouds, called planetary nebulae, have nothing to do with planets. The name came from 18th century astronomers who thought they looked like distant worlds through their primitive telescopes. In reality, each nebula is a stellar death shroud, the outer layers of a sun-like star blown into space during its final moments. The process begins when a star exhausts the nuclear fuel in its core. For billions of years, the star has maintained a delicate balance between the inward pull of gravity and the outward pressure of nuclear fusion. But when the fuel runs out, gravity wins. The core collapses and heats up, while the star's outer layers expand and cool, transforming the once stable star into a bloated red giant. As the red giant phase continues, the star becomes increasingly unstable. Thermal pulses deep in its core send shockwaves rippling through the stellar atmosphere. These pulses blow off the star's outer layers in a series of gentle puffs, like cosmic smoke rings expanding into space. The ejected material forms a hollow shell around the dying star, initially invisible in the cold darkness. Then comes the transformation that creates the beauty we see. The star's core, now exposed as a white dwarf, burns at temperatures exceeding 100,000 degrees. This stellar ember floods the expanding shell with ultraviolet radiation so intense it strips electrons from atoms in the surrounding gas. The ionized hydrogen glows red, while oxygen emits green and blue light. The result is a cosmic stained glass window painted in impossible colors. Each planetary nebula tells a unique story of stellar death. Some form perfect spheres, their gas expanding uniformly in all directions. Others create intricate patterns, hourglass shapes, or butterfly wings, sculpted by magnetic fields and companion stars. The most complex nebulae resemble cosmic flowers, with delicate petals of glowing gas arranged in symmetrical patterns that rival any artwork created by human hands. The timescales involved are both vast and fleeting. The dying star took billions of years to reach this point, burning steadily through most of the universe's history. But the planetary nebula phase lasts only tens of thousands of years, a cosmic blink of an eye. The expanding shell gradually disperses into the interstellar medium, enriching the galaxy with heavy elements forged in the star's core. These elements become the building blocks for future generations of stars and planets. The carbon in our DNA, the nitrogen in our atmosphere, the phosphorus in our bones, all were created in the nuclear furnaces of dying stars and distributed through planetary nebulae. We are literally made of star stuff, recycled cosmic material that once glowed in nebulae like these. The white dwarf at the nebula's center will continue to shine for trillions of years, slowly cooling from white-hot to red, to brown, to black. It's a preview of our own sun's fate, destined to follow the same path when it exhausts its fuel 5 billion years from now. Our sun will swell into a red giant, engulf the inner planets, and then cast off its outer layers in a final act of cosmic artistry. In the heart of Triangulum's most active star-forming regions, blue supergiants burn like cosmic torches, racing toward their own destruction. These stellar giants represent the ultimate paradox of stellar evolution. They're the most massive, most luminous, and most spectacular stars in the galaxy. Yet they live the shortest lives. A blue supergiant burns through its nuclear fuel like a Formula One car burning rubber, converting 4 million tons of matter into energy every second. The nuclear furnace in its core reaches temperatures of 50 million degrees, hot enough to fuse elements all the way up to iron. The star's surface temperature exceeds 40,000 degrees, nearly 7 times hotter than our sun. This extreme heat gives the star its characteristic blue-white color and makes it shine with the brightness of 100,000 suns. The stellar wind it produces is so powerful it strips away material at rates that would completely evaporate our sun in just a few million years. These giants are essentially living on borrowed time from the moment they ignite. While our sun will burn steadily for 10 billion years, a blue supergiant exhausts its hydrogen fuel in just 3 to 5 million years. It's like comparing a sip of water to a fire hose, both drawn from the same reservoir, but consumed at vastly different rates. The star's death throes begin in its core, where nuclear fusion has built up layers of increasingly heavy elements. Hydrogen fuses to helium, helium to carbon, carbon to oxygen, oxygen to silicon, and finally, silicon to iron. Each fusion stage releases less energy than the previous one, like a fire burning through progressively damper wood. When the core starts producing iron, the star's fate is sealed. Iron cannot fuse to release energy. It can only absorb it. The nuclear furnace that has supported the star for millions of years suddenly becomes an energy sink. The core temperature plummets, and with it, the outward pressure that has held the star together against its own gravity. What happens next occurs faster than a human heartbeat. The core collapses from the size of Earth to the size of a city in less than a second. The density becomes so extreme that protons and electrons are crushed together to form neutrons. The collapsing matter rebounds off this neutron core like a rubber ball hitting concrete, creating a shockwave that rips through the star's outer layers. The explosion that follows can outshine an entire galaxy in a matter of seconds. The supernova releases more energy than our sun will produce in its entire 10 billion year lifetime. The blast wave expands at speeds of 30,000 kilometers per second, heating the surrounding gas to temperatures exceeding 1 billion degrees. The supernova enriches the galaxy with heavy elements forged in the star's core and during the explosion itself. Elements heavier than iron, including gold, platinum, and uranium, are created only in these violent stellar deaths. The shockwave also triggers star formation in nearby gas clouds, seeding the galaxy with the next generation of stars. What remains after the explosion depends on the star's original mass. Stars between 8 and 25 times the mass of our Sun leave behind neutron stars. Objects so dense that a teaspoon of neutron star material would weigh as much as Mount Everest. More massive stars collapse into black holes, regions of space-time where gravity is so strong that not even light can escape. Surrounding every star, every gas cloud, every bright spiral arm in the Triangulum galaxy is a vast scaffolding built from matter we cannot see or touch. Dark matter makes up 85% of all matter in the universe. Yet it interacts with ordinary matter only through gravity. It doesn't emit light, doesn't absorb light, and doesn't reflect light. It's like trying to map an invisible city by watching how people move through its streets, inferring the locations of buildings from the patterns of foot traffic. The first clues to dark matter's existence came from studying galaxy rotation curves. When astronomers measured how fast stars orbit the galactic center, they discovered something impossible. According to the visible matter in the galaxy, stars in the outer regions should move much slower than those near the center, just like planets in our solar system. But the observations showed something different. Stars throughout the galaxy move at nearly the same speed, regardless of their distance from the center. It's like watching a merry-go-round where all the horses gallop at the same pace, whether they're on the inner ring or the outer edge. The only way to explain this is if the galaxy contains 5 times more mass than we can see. This invisible mass forms a roughly spherical halo around the galaxy, extending far beyond the visible stars. Computer simulations show that without this dark matter halo, the Triangulum galaxy would have torn itself apart billions of years ago. The spiral arms would have unwound, the gas would have been flung into intergalactic space, and star formation would have ceased. The dark matter halo acts like a cosmic gravitational net, holding the galaxy together while remaining completely invisible. It's the ultimate cosmic construction project, a scaffold built from exotic particles that don't interact with ordinary matter except through their gravitational influence. But what exactly is dark matter? The honest answer is that we don't know. It could be composed of weakly interacting massive particles, hypothetical entities that were predicted by particle physics theories but have never been detected. It could be actions, incredibly light particles that barely interact with anything. Or it could be something completely unexpected, a form of matter so alien that our current physics cannot even describe it. The mystery deepens when we realize that dark matter was crucial to the formation of the universe itself. In the early cosmos, tiny fluctuations in the dark matter density grew under their own gravity, creating the first structures in the universe. These dark matter halos became the seeds around which galaxies formed, providing the gravitational wells that allowed ordinary matter to collapse and ignite the first stars. Without dark matter, the universe would be a very different place. Galaxies would be smaller and less stable. Star formation would be less efficient. The cosmic web of filaments and voids that connects galaxies across billions of light years would never have formed. We might be living in a universe with no large-scale structure at all, just isolated stars drifting through empty space. The search for dark matter has become one of the greatest detective stories in science. Deep underground laboratories shield sensitive detectors from cosmic rays, waiting for the telltale signature of a dark matter particle collision. Particle accelerators smash protons together at nearly the speed of light, hoping to create dark matter particles in high-energy collisions. Space telescopes scan the cosmos for the gravitational signatures of dark matter clumps. Yet, despite decades of searching, dark matter remains as elusive as ever. It's everywhere and nowhere, holding the universe together while remaining completely invisible to our instruments. Deep within the Triangulum Galaxy's spiral arms, cosmic nurseries blaze with the light of millions of newborn suns. The largest of these star-forming regions, NGC 604, shines with a combined brightness of 600,000 stars like our Sun. This single stellar nursery contains enough energy to power our entire solar system for billions of years. From a distance, it appears as a rosy glow against the dark backdrop of space. But up close, it reveals itself as a churning cauldron of creation and destruction. The region spans more than 1,000 light-years, making it larger than the distance between our Sun and the nearest star. Within this vast expanse, gravity is sculpting the raw materials of space into the next generation of stars. Towering pillars of gas and dust, some reaching heights of several light-years, serve as stellar incubators where new suns are taking their first breaths. These pillars are both beautiful and temporary. They're carved by the intense radiation and stellar winds from nearby massive stars, which act like cosmic sandblasters, eroding the gas columns while simultaneously triggering new star formation within them. The process is a delicate balance between creation and destruction, with each new star contributing to the forces that will eventually disperse the very cloud that gave it birth. The youngest stars in these regions are still embedded in their birth cocoons, visible only in infrared light that can penetrate the surrounding dust. These stellar embryos are fed by accretion disks of swirling material that spiral inward, growing hotter and brighter as they approach the star's surface. Some of these disks may be forming planetary systems, laying the groundwork for future worlds. The most massive stars in these regions burn so brightly they ionize the surrounding gas, creating glowing bubbles of plasma that expand like cosmic soap bubbles. These emission nebulae paint the star-forming regions in vibrant colors, with red hydrogen, blue oxygen, and green doubly ionized oxygen, creating a palette that would make any artist envious. The energy output from these stellar nurseries is staggering. A single massive star can produce as much energy in 1 second as our Sun produces in an entire year. When dozens or hundreds of these giants form in the same region, they create stellar associations that can outshine entire galaxies. The radiation pressure from these young stars is so intense it can blow away the remaining gas in the region, effectively shutting down further star formation. But the influence of these stellar nurseries extends far beyond their visible boundaries. The hot gas they produce rises above the galactic disk, creating fountains of enriched material that rain back down onto the galaxy. This galactic fountain carries heavy elements forged in stellar cores to regions where they can be incorporated into the next generation of stars and planets. The stellar winds from massive stars collide and interact, creating superbubbles of hot gas that can grow to hundreds of light-years in diameter. These bubbles serve as cosmic mixing bowls, stirring the interstellar medium and distributing heavy elements throughout the galaxy. When the most massive stars explode as supernovas, they add even more energy to these bubbles, sometimes breaking through the galactic disk entirely. The life cycle of a star-forming region follows a predictable pattern. It begins with the gravitational collapse of a giant molecular cloud. Triggered by some external disturbance, star formation proceeds rapidly, with the most massive stars forming first. These giants quickly begin to disrupt their birth environment, carving out cavities in the gas and eventually dispersing the cloud entirely. The entire process takes only 10 to 20 million years, a brief moment in galactic time. But during this cosmic instant, these stellar nurseries transform the galaxy, enriching it with heavy elements and organizing the interstellar medium into the complex structures we observe today. Orbiting the Triangulum galaxy like ancient sentinels are stellar time capsules that preserve the memory of the universe's youth. Globular clusters are among the oldest objects in the galaxy. Spherical collections of hundreds of thousands to millions of stars bound together by their mutual gravity. These stellar cities formed when the universe was less than 1 billion years old, making them living fossils from the cosmic dawn. Each cluster tells a story that spans nearly the entire history of the cosmos. The stars within these clusters are all roughly the same age, born from the same primordial gas cloud in a single burst of star formation. Unlike the star-forming regions we see today, these ancient stellar nurseries were composed almost entirely of hydrogen and helium, the simplest elements forged in the Big Bang. Heavy elements like carbon, oxygen, and iron were virtually absent, creating a generation of stars unlike any being born today. This chemical purity makes globular cluster stars living laboratories for understanding stellar evolution. Without heavy elements to complicate their nuclear fusion processes, these stars follow predictable evolutionary paths. The most massive stars have long since exploded as supernovas or evolved into white dwarfs, leaving behind populations of smaller, longer-lived stars that will shine for trillions of years. The Triangulum galaxy hosts several dozen globular clusters, each containing clues about the galaxy's formation and early history. These clusters didn't form where we see them today. When they were born, the galaxy was a chaotic, turbulent place, with gas clouds colliding and merging in a cosmic dance of destruction and creation. The clusters formed in the dense cores of these colliding clouds, then survived the galaxy's violent youth to become the ancient relics we observe today. The distribution of globular clusters around the galaxy reveals the shape of the dark matter halo that surrounds it. Unlike the stars in the galactic disk, which follow circular orbits, globular clusters trace elongated, elliptical paths that carry them far above and below the galactic plane. These orbits map out the three-dimensional structure of the galaxy's invisible dark matter scaffolding. Each cluster is a gravitational masterpiece, with stars packed so densely that the night sky from a planet within the cluster would be ablaze with thousands of bright stars. The gravitational interactions between these stars create a complex dance where stellar encounters can fling stars out of the cluster or cause them to spiral inward toward the center. Over billions of years, this gravitational evolution has sculpted the clusters into the perfect spherical shapes we observe today. The cores of globular clusters harbor some of the most exotic objects in the universe. Neutron stars, the ultra-dense remnants of supernova explosions, can be found spinning rapidly as pulsars, lighthouse-like beacons that sweep the galaxy with beams of radiation. Some clusters may even contain intermediate-mass black holes, objects too massive to form from a single stellar collapse, but too small to be the supermassive black holes found at galactic centers. But perhaps the most remarkable aspect of globular clusters is their role as cosmic chronometers. By studying the colors and brightness of stars within these clusters, astronomers can determine their ages with precision. The oldest clusters in the Triangulum galaxy are nearly 13 billion years old, formed when the universe was less than 1 billion years old. They're among the first generation of stellar systems to form after the Big Bang. These ancient stellar cities have witnessed the entire history of galaxy formation. They've seen the galaxy grow from a small, chaotic collection of gas clouds into the majestic spiral we observe today. They've survived countless close encounters with other clusters, the disruption of galactic mergers, and the gradual chemical enrichment of the galaxy through successive generations of star formation. The elegant spiral arms of the Triangulum galaxy aren't just beautiful decorations. They're cosmic highways that channel the flow of matter and energy across tens of thousands of light years. From our perspective, the galaxy's spiral structure appears static and permanent, like a frozen whirlpool in space. But this is an illusion created by the vast timescales involved. The spiral arms are actually waves of compression traveling through the galactic disk, similar to traffic jams that move along a highway, even though individual cars enter and exit the jam. This phenomenon, called spiral density wave theory, explains one of the galaxy's most puzzling features. If the spiral arms were simply material structures rotating with the galaxy, they would have wound up completely after just a few rotations, destroying the spiral pattern. Instead, the arms persist because they're pressure waves, regions where the density of stars and gas is temporarily higher than average. As material orbits the galaxy, it encounters these density waves like a car approaching a traffic jam. The gas clouds slow down, compress, and pile up in the spiral arms. This compression triggers star formation, lighting up the arms with bright young stars and glowing nebulae. The most massive stars burn out quickly, fading before they can move far from their birth sites, which is why the spiral arms appear so prominently in blue light. The process creates a cosmic conveyor belt of star formation. Gas flows into the spiral arms from the spaces between them, gets compressed into dense clouds, forms stars, and then disperses as stellar winds and supernova explosions blow the remaining gas back into the inter-arm regions. This cycle repeats every few 100 million years as the galaxy rotates. The spiral arms also act as cosmic rivers, channeling gas from the outer galaxy toward the center. This radial flow of material helps explain how galaxies can maintain star formation over billions of years. Without this inward transport of gas, the central regions would quickly exhaust their fuel for making new stars. But the spiral structure isn't perfectly stable. Computer simulations show that spiral arms can strengthen, weaken, split, and merge over time. The Triangulum galaxy's current two-arm spiral pattern may be temporary, possibly the result of a recent gravitational interaction with a neighboring galaxy or the passage of a massive gas cloud. The arms also create different environments within the galaxy. The spaces between the spiral arms are relatively quiet, with lower rates of star formation and fewer supernova explosions. These inter-arm regions may be more hospitable to the development of complex life, shielded from the intense radiation and stellar violence that characterizes the spiral arms themselves. The magnetic field of the galaxy follows the spiral structure, creating invisible highways for charged particles, cosmic rays, high-energy particles accelerated by supernova explosions. Follow these magnetic field lines as they propagate through the galaxy. This creates a complex three-dimensional structure where the visible spiral arms are just one component of a much larger architectural framework. The spiral arms also influence the chemical evolution of the galaxy. Star formation in the arms produces heavy elements that are dispersed by stellar winds and supernova explosions. These elements mix with the interstellar medium and eventually make their way to the inter-arm regions, where they can be incorporated into the next generation of stars. This creates a gradient of heavy element abundance that varies both with distance from the galactic center and with position relative to the spiral arms. Recent observations have revealed that the spiral arms may be more dynamic than previously thought. Some regions show evidence of spur-like structures branching off from the main arms, creating a more complex pattern than the simple two-arm spiral. These features may be temporary, created by local instabilities in the galactic disk or by the gravitational influence of massive star-forming regions. At the center of the Triangulum galaxy lies a region so dense with stars and shrouded in dust that we're only beginning to understand its true nature. The galactic core, or nucleus, represents less than 1% of the galaxy's total volume, but contains a disproportionate share of its most exotic phenomena. Here, stars are packed together at densities thousands of times higher than in our solar neighborhood. The night sky from a planet in this region would be ablaze with brilliant stars, many bright enough to cast shadows. Unlike the supermassive black holes that lurk at the centers of larger galaxies, the Triangulum galaxy's core appears to lack such a monster. This makes it unusual among spiral galaxies, most of which harbor central black holes containing millions or billions of times the mass of our Sun. The absence of a supermassive black hole suggests that the Triangulum galaxy may have had a different evolutionary history than its larger cousins. Instead of a central black hole, the core region contains a dense concentration of older stars, many of them red giants and supergiants that have evolved beyond their main sequence lifetimes. These stellar elders dominate the infrared light from the galactic center, creating a warm glow that can be detected even through the obscuring dust clouds that surround the region. The dust itself tells a story of stellar death and renewal. Much of it consists of heavy elements forged in the cores of dying stars and dispersed through supernova explosions and stellar winds. Silicon, carbon, and iron atoms that were created in stellar furnaces now drift as microscopic grains through the interstellar medium, absorbing and scattering starlight. This dust creates a cosmic fog that makes the galactic center one of the most challenging regions to study. Visible light from the core stars is almost completely absorbed, forcing astronomers to rely on infrared and radio observations that can penetrate the dusty veil. Each new wavelength reveals different aspects of the core's structure and activity. Recent infrared surveys have revealed an unexpected level of star formation activity in the central region, despite the apparent lack of a supermassive black hole. The core shows signs of recent stellar births, with young, hot stars scattered throughout the older stellar population. This suggests that gas is still flowing into the center and collapsing to form new stars, possibly triggered by spiral arm dynamics or past gravitational interactions. The core also contains several unusual stellar objects that may be the products of the extreme environment. Close stellar encounters in the dense core can strip matter from one star and transfer it to another, creating exotic binary systems and stellar remnants. Some of these objects may be blue stragglers, stars that appear younger than their surroundings because they have been rejuvenated by mass transfer or stellar mergers. X-ray observations have revealed another layer of complexity in the galactic center. Hot gas with temperatures exceeding millions of degrees creates a diffuse glow that extends throughout the core region. This gas may be heated by shock waves from supernova explosions or by the collective stellar winds from the massive stars in the region. The magnetic field in the galactic core is particularly strong and complex, twisted into intricate patterns by the rotation of the galaxy and the turbulent motions of the gas. These magnetic fields may play a crucial role in channeling gas flows and influencing star formation rates in the central region. Perhaps most intriguingly, the core shows evidence of past violent activity. Expanding shells of hot gas suggest that the region has experienced periods of enhanced star formation and supernova activity in the past. These starbursts may have been triggered by gravitational interactions with other galaxies, or by the infall of large gas clouds from the outer regions. In the heart of the Triangulum galaxy's most active regions, Stellar metropolises burn with the collective light of millions of suns. These massive star clusters, some containing over 1 million individual stars, shine so brightly they can be seen from billions of light years away. The largest of these stellar cities, known as superclusters, pack more luminous mass into a few dozen light years than our entire local galactic neighborhood contains in 1,000 light years. The most spectacular of these clusters formed in violent bursts of star formation, triggered by galactic collisions or the passage of massive gas clouds. When conditions are just right, a single molecular cloud can collapse to form not just a few scattered stars, but an entire stellar civilization all at once. The gravitational collapse happens so rapidly that millions of stars ignite within a few million years, creating a stellar fireworks display that outshines entire dwarf galaxies. These newborn stellar cities are dominated by the most massive stars in the universe. Blue and white supergiants that burn with temperatures exceeding 50,000 degrees. The combined radiation from these stellar titans creates a pressure so intense it can blow away entire star-forming regions, carving out vast cavities in the interstellar medium. The energy output from a single massive cluster can exceed the luminosity of 100 million stars like our Sun. The clusters themselves are gravitational masterpieces, with stars orbiting their common center of mass in complex patterns that have been refined over millions of years. The most massive stars sink toward the center through gravitational interactions, while smaller stars are flung toward the outer regions. This process, called mass segregation, creates a stellar hierarchy where the biggest and brightest stars dominate the cluster's core. But these stellar cities are not permanent fixtures. The same massive stars that make them so luminous also seal their fate. Within just a few million years, the most massive stars begin to explode as supernovas, adding their energy to the stellar winds that are already pushing against the cluster's boundaries. Each supernova explosion sends shockwaves rippling through the cluster, potentially triggering new star formation while simultaneously dispersing the gas that could fuel future stellar births. The most violent clusters experience what astronomers call a supernova chain reaction. One massive star explodes, compressing nearby gas clouds and triggering the formation of even more massive stars. These new giants burn through their fuel rapidly and explode in turn, creating a cascade of stellar death that can illuminate the entire cluster for thousands of years. Some of these stellar cities are so massive, they approach the boundary between star clusters and dwarf galaxies. The largest contain enough material to form their own gravitational wells, trapping gas and dust that can fuel multiple generations of star formation. These objects blur the line between stellar associations and true galaxies, representing a transitional class of cosmic structures. The stellar winds from massive clusters create super bubbles of hot gas that can grow to thousands of light years in diameter. These bubbles serve as cosmic laboratories where the interstellar medium is heated, compressed, and enriched with heavy elements. The expanding shells of gas eventually break through the galactic disk, creating fountains of hot material that rain back down onto the galaxy. The light from these stellar cities can be seen across vast distances, serving as beacons that mark the locations of the most active star-forming regions in the universe. When we observe distant galaxies, the bright knots of light we see are often massive star clusters similar to those in the Triangulum galaxy, cosmic lighthouses that guide our understanding of galactic evolution. Scattered throughout the Triangulum galaxy are vast hollows in space, cosmic caverns carved by the violent deaths of massive stars. These supernova remnants are the expanding shells of debris left behind when stars explode with the force of 10 billion hydrogen bombs detonating every second for millions of years. The blast waves from these explosions race through space at speeds exceeding 10,000 kilometers per second, sweeping up interstellar gas and dust like cosmic snowplows. The process begins with a catastrophic collapse. When a massive star exhausts its nuclear fuel, its core implodes in less than a second, rebounding in an explosion that can outshine an entire galaxy. The shockwave from this explosion rips through the star's outer layers, heating them to temperatures exceeding 1 billion degrees and flinging them into space at a significant fraction of the speed of light. This expanding shell of stellar debris crashes into the surrounding interstellar medium like a cosmic tsunami. The collision creates a double shockwave system, with one shock moving outward into the interstellar gas and another moving inward through the ejected stellar material. The region between these shocks becomes a furnace where gas is heated to millions of degrees, creating a glowing bubble of plasma that can be detected across the electromagnetic spectrum. The supernova remnant grows larger and fainter as it expands, eventually reaching diameters of hundreds of light years. During this evolution, the remnant acts as a cosmic particle accelerator, using magnetic fields and shock waves to accelerate particles to nearly the speed of light. These cosmic rays then propagate throughout the galaxy, carrying energy and information about stellar explosions across vast distances. The shapes of supernova remnants tell stories of stellar violence and interstellar architecture. Some form perfect spheres, expanding uniformly in all directions through a homogeneous medium. Others create complex filamentary structures that trace the magnetic field lines and density variations in the surrounding space. The most spectacular remnants form intricate, lacework patterns of glowing gas, with delicate filaments and knots that reveal the turbulent physics of shockwave propagation. These cosmic caverns have profound effects on their galactic neighborhoods. The hot gas they create rises above the galactic disk, forming chimneys and fountains that transport heavy elements from the disk to the galactic halo. This process helps regulate the chemical evolution of the galaxy, ensuring that elements forged in stellar cores are distributed throughout the galactic ecosystem. The energy injection from supernova remnants also influences star formation rates in nearby regions. The shock waves can trigger the collapse of molecular clouds, initiating new episodes of stellar birth. But the same explosions can also disrupt star-forming regions, heating the gas to temperatures too high for gravitational collapse. This creates a complex feedback loop, where stellar death influences stellar birth across multiple generations. Some supernova remnants interact with each other, creating superbubbles when multiple explosions occur in the same region. These enormous cavities can grow to thousands of light years in diameter, dominating the structure of the interstellar medium over vast regions. The largest superbubbles can break through the galactic disk entirely, creating pathways for gas to flow between the disk and the halo. Throughout the Triangulum galaxy, millions of binary star systems perform an elegant gravitational ballet that will end in violence. More than half of all stars in the galaxy are born in pairs or groups, locked in orbital embraces that can last billions of years. These cosmic couples dance around their common center of mass, their gravitational attraction maintaining a delicate balance between approaching too close and drifting apart. But this celestial waltz is not eternal. Time, stellar evolution, and the inexorable pull of gravity conspire to create endings more dramatic than any terrestrial tragedy. The most common fate awaits systems where one star is significantly more massive than its companion. The massive star evolves faster, exhausting its nuclear fuel first and swelling into a red giant. As it expands, its outer layers reach the point where the companion star's gravity becomes stronger than its own. Material begins to flow from the giant to its smaller partner, creating a bridge of glowing gas between the two stars. This mass transfer fundamentally changes both stars. The donor star loses mass and can actually extend its lifetime by shedding its outer layers. The recipient star, meanwhile, gains mass and brightens dramatically. In some cases, the infalling material forms an accretion disk around the smaller star, heating up to millions of degrees and creating a brilliant source of X-rays. The mass transfer process is rarely smooth or steady. The flow of material can be unstable, creating nova explosions when enough hydrogen accumulates on the surface of the receiving star. These novae can temporarily make the system 10,000 times brighter than normal, creating stellar fireworks that can be seen from great distances across the galaxy. But some binary systems are destined for even more spectacular endings. When both stars are massive enough to form neutron stars or black holes, the system enters a death spiral that can last millions of years. The two compact objects orbit each other with increasing speed, their orbital energy carried away by gravitational waves that ripple through the fabric of space-time itself. As the orbit shrinks, the two objects spiral inward, like water circling a drain. The final moments of this cosmic dance occur in a matter of seconds, with the neutron stars or black holes orbiting each other hundreds of times per second before finally colliding. The merger releases more energy in gravitational waves than all the visible stars in the observable universe combined. These kilonova explosions create conditions so extreme they forge heavy elements that cannot be produced in normal stellar cores. Gold, platinum, and uranium are created in the intense heat and pressure of the merger, then scattered into the interstellar medium where they can be incorporated into future generations of stars and planets. The gold in our jewelry, the platinum in our electronics, all may have been forged in the violent merger of neutron stars billions of years ago. The Triangulum galaxy hosts thousands of these binary systems at various stages of their evolution. Some are just beginning their dance. Young pairs of stars that will orbit each other for billions of years. Others are approaching their final acts, with white dwarf stars slowly consuming their companions, or neutron stars, spiraling toward merger. The study of binary star evolution has revealed that stellar death is far more complex and violent than once thought. Single stars may end their lives quietly, fading into white dwarf obscurity. But binary systems can experience multiple episodes of mass transfer, nova explosions, and ultimately, catastrophic mergers that reshape the galaxy around them. Across the Triangulum galaxy, dying stars create masterpieces that rival the greatest works of art ever conceived by human imagination. These planetary nebulae are cosmic paint palettes where physics becomes artistry. Each nebula displays a unique combination of colors created by different elements glowing at specific temperatures and densities. The red glow comes from hydrogen, the universe's most abundant element, while oxygen produces ethereal blues and greens. Nitrogen adds touches of deep red, and sulfur contributes yellows and oranges to the cosmic canvas. But the true artistry lies in the nebula's structure, shaped by forces as complex as any master painter's technique. The dying star at the center doesn't simply puff off its outer layers uniformly. Instead, magnetic fields, stellar rotation, and the presence of companion stars sculpt the expanding gas into intricate patterns that defy easy explanation. Some nebulae form perfect rings, like cosmic smoke rings expanding through space. Others create hourglass shapes, with narrow waists and bulbous ends that suggest the influence of equatorial disks around the central star. The most complex nebulae resemble butterflies, flowers, or even human eyes, with symmetrical patterns that seem almost intentionally designed. The Helix Nebula, sometimes called the Eye of God, demonstrates the incredible precision of these cosmic sculptures. Its intricate, braided structure contains thousands of individual knots and filaments, each one a story of gas compression and magnetic field interaction. The nebula's colors shift from deep red at the edges to a brilliant blue-green in the center, creating a three-dimensional artwork that spans several light years. The creation of these colors involves quantum physics at its most fundamental level. When the central white dwarf star bombards the surrounding gas with ultraviolet radiation, it strips electrons from atoms, ionizing the gas and causing it to glow. Each element glows at specific wavelengths determined by the energy levels of its electrons. The result is a spectrum of colors that serves as a fingerprint for the elements present in the nebula. The intensity and distribution of these colors reveal the history of the dying star. Red regions indicate areas where the ultraviolet radiation is weaker, allowing hydrogen to remain partially neutral. Blue-green regions mark zones of intense ionization, where oxygen atoms have been stripped of multiple electrons. The boundaries between different colored regions trace the shock fronts and density variations within the expanding gas. Some nebulae change their appearance over human timescales, allowing astronomers to watch the cosmic artwork evolve in real time. The expansion of the gas shells creates moving patterns of light and shadow as different regions brighten and fade. Knots of denser gas can be seen streaming away from the central star like cosmic fireworks, while cavities carved by stellar winds create hollow spheres within the larger nebula. The symmetry of many planetary nebulae suggests that binary star systems play a crucial role in their formation. A companion star orbiting the dying giant can create jets of gas that punch through the stellar envelope, creating the bipolar structures seen in many nebulae. The gravitational influence of the companion can also create spirals and rings as the gas is shaped by orbital dynamics. These cosmic artworks are temporary, lasting only tens of thousands of years before the expanding gas becomes too diffuse to glow brightly. But in that brief moment of cosmic time, they transform the ordinary death of a star into something transcendent, creating beauty from destruction and order from chaos. In the most violent star-forming regions of the Triangulum galaxy, stellar monsters are literally blowing themselves apart. Wolf-Rayet stars are among the most extreme objects in the universe. Massive suns that have been stripped down to their nuclear burning cores by their own stellar winds. These stellar hurricanes rage at speeds exceeding 2,000 kilometers per second, carrying away the equivalent of Earth's entire mass every year. The winds are so powerful they can be detected from thousands of light years away, creating expanding bubbles of hot gas that dwarf entire solar systems. These stellar extremists begin their lives as the most massive stars in the galaxy, giants containing 50 to 100 times more mass than our Sun. But their enormous size becomes their weakness. The nuclear fusion in their cores burns so fiercely that the radiation pressure pushes against their outer layers with incredible force. Eventually, this pressure overcomes the star's gravitational grip, launching the outer atmosphere into space at hypersonic speeds. The stellar wind from a Wolf-Rayet star is not a gentle breeze, but a hurricane of atomic particles. The mass loss rate can exceed 1/1,000,000th of a solar mass per year, meaning these stars lose the equivalent of our entire Sun's mass in just a few million years. The expelled material carries away not just mass, but also angular momentum, causing the star to spin faster as it shrinks, like a figure skater pulling in their arms. What remains after this stellar stripping is a naked stellar core, burning helium and heavier elements in a nuclear furnace that reaches temperatures of 100 million degrees. The surface temperature of these exposed cores can exceed 50,000 degrees, making them some of the hottest stars known. They shine with a brilliant blue-white light that ionizes gas across vast distances, creating glowing nebulae that can be seen from outside the galaxy. The stellar winds from Wolf-Rayet stars don't expand uniformly. Instead, they create complex structures shaped by the star's magnetic field, rotation, and the presence of companion stars. Some winds form spiral patterns as they interact with binary companions, while others create bipolar outflows that shoot jets of material in opposite directions. The most spectacular Wolf-Rayet nebulae resemble cosmic roses or butterflies, with delicate petals of glowing gas arranged in beautiful, symmetrical patterns. These stellar winds carry heavy elements forged in the star's core out into the interstellar medium. Carbon, oxygen, and nitrogen produced by nuclear fusion are dispersed across the galaxy, enriching the raw materials for future star formation. Some Wolf-Rayet stars produce so much carbon that they create sooty dust, painting dark silhouettes against the bright background of star-forming regions. The interaction between Wolf-Rayet winds and the surrounding interstellar medium creates some of the most energetic phenomena in the galaxy. When these high-speed winds collide with nearby gas clouds, they create shockwaves that can trigger new episodes of star formation. The winds can also carve out vast cavities in the interstellar medium, creating bubble-like structures that can grow to hundreds of light years in diameter. But the most dramatic aspect of Wolf-Rayet evolution is how it ends. Having stripped away their outer layers, these stars have exposed their cores to space, creating conditions that lead to some of the most violent explosions in the universe. The lack of a massive hydrogen envelope means that when these stars finally explode as supernovas, they produce different types of explosions than normal massive stars. Some Wolf-Rayet stars may produce hypernova explosions, events so energetic they can create gamma-ray bursts that outshine entire galaxies. These explosions are thought to be the birth sites of the most massive black holes, and may be responsible for some of the heaviest elements in the universe. Scattered throughout the Triangulum galaxy's spiral arms are stellar neighborhoods that are slowly dissolving, their members drifting apart like leaves scattered by an autumn wind. Open star clusters are the galaxy's most fragile communities, loose associations of hundreds to thousands of stars born from the same molecular cloud. Unlike the ancient, tightly bound globular clusters that orbit the galaxy's halo, these younger stellar groups are held together by weak gravitational bonds that weaken over time. They represent stellar families in the process of breaking apart, each member eventually destined to wander the galaxy alone. The dissolution process begins almost immediately after the cluster forms. The most massive stars, which sink toward the cluster's center through gravitational interactions, live fast and die young. When they explode as supernovas, they remove mass from the cluster and can even kick other stars out of the system entirely. Each stellar death weakens the cluster's gravitational grip on its remaining members. Meanwhile, the galaxy itself conspires against these stellar communities. As the cluster orbits the galactic center, it encounters tidal forces from the galaxy's gravitational field. These forces stretch the cluster, pulling stars away from its outer edges like ocean tides pulling sand from a beach. The process is gradual but relentless, stripping away the cluster's least bound members over millions of years. The cluster's journey through the galaxy also exposes it to gravitational perturbations from giant molecular clouds, spiral arms, and other stellar systems. Each encounter can scatter cluster members, sending them on new orbits that may never bring them back to their stellar family. It's like a cosmic game of billiards, where chance encounters determine which stars remain together and which are sent wandering into the galactic wilderness. Some clusters dissolve faster than others, depending on their initial mass density, and location in the galaxy. Clusters born in the dense central regions of the galaxy face stronger tidal forces and more frequent encounters with other objects. Those formed in the outer regions may survive longer, but they too eventually succumb to the galaxy's disruptive influences. The Hyades cluster, one of the nearest open clusters to our solar system, exemplifies this dissolution process. The cluster's core still contains dozens of stars that share a common motion through space. But its outer regions have been stripped away over the past few 100 million years, scattered throughout our local galactic neighborhood. We've identified individual stars that were once part of the Hyades, but have now drifted too far from their siblings to be easily recognized as cluster members. The dissolution of open clusters contributes to the galaxy's chemical evolution. Each cluster contains stars with similar ages and compositions, forged from the same primordial gas cloud. As these stars disperse throughout the galaxy, they carry with them the chemical signatures of their birth environments. The heavy elements they produce through nuclear fusion and stellar winds become mixed with the broader galactic medium, creating the complex chemical patterns we observe today. Some dissolved clusters leave behind streams of stars that share similar motions and compositions, creating moving groups that can be traced across the galaxy. These stellar streams are like fossil records of ancient cluster dissolution, allowing astronomers to reconstruct the history of stellar formation and dispersal over cosmic time. The study of cluster dissolution has revealed that the galaxy's stellar population is far more dynamic than once thought. Stars don't simply orbit the galactic center in isolation, but are part of complex flows and streams that reflect the galaxy's violent history. The Sun itself may have been born in an open cluster that dissolved billions of years ago, scattering its stellar siblings across the galaxy. Flowing through the vast spaces between stars is an invisible ocean that connects every corner of the Triangulum galaxy in a complex web of matter and energy. The interstellar medium is far from empty space. This cosmic ocean contains roughly 1 atom per cubic centimeter, a density so low it would be considered a perfect vacuum by terrestrial standards. Yet across the galaxy's 60,000 light-year diameter, this tenuous material adds up to billions of solar masses of gas and dust, equal to about 10% of all the matter in the galaxy. This invisible ocean exists in multiple phases, each with its own temperature, density, and dynamics. The coldest regions are giant molecular clouds, where temperatures barely exceed absolute zero and hydrogen atoms combine to form molecules. These clouds are the galaxy's stellar nurseries, dense enough to collapse under their own gravity and give birth to new stars. Between these cold clouds flows a warm medium of neutral hydrogen, heated by starlight and cosmic rays to temperatures of several thousand degrees. This material fills much of the galaxy's volume, creating a tenuous atmosphere that permeates the space between star systems. It's like the air in a vast cosmic cathedral, invisible but essential to the structure of the whole. The hottest phase of the interstellar medium reaches temperatures exceeding 1 million degrees. Created by supernova explosions and stellar winds from massive stars, this superheated plasma forms bubbles and cavities that can grow to hundreds of light years in diameter, creating a frothy structure that resembles cosmic sea foam. The hot gas rises above the galactic disk, creating fountains and chimneys that connect the disk to the galaxy's extended halo. These different phases don't exist in isolation, but are constantly interacting, trading mass and energy in a complex dance of thermodynamics. Cold clouds can be heated by shock waves from supernovas, while hot gas can cool and condense to form new molecular clouds. The result is a dynamic ecosystem where the conditions for star formation are constantly changing. The interstellar medium also serves as the galaxy's circulatory system, transporting heavy elements forged in stellar cores throughout the galactic ecosystem. When massive stars explode as supernovas, they inject carbon, oxygen, silicon, and iron into the surrounding medium. These elements mix with the existing gas, gradually enriching the galaxy's chemical composition and providing the raw materials for rocky planets and life itself. Magnetic fields thread through this cosmic ocean, creating invisible highways for charged particles and influencing the flow of gas on galactic scales. These magnetic fields can accelerate particles to nearly the speed of light, creating the cosmic rays that permeate the galaxy. They can also channel the flow of gas, creating filamentary structures that connect distant regions of the galaxy. The interstellar medium is also pervaded by radiation from stars, cosmic rays, and the cosmic microwave background. This radiation field provides the energy that ionizes atoms, dissociates molecules, and drives the chemical reactions that create complex molecules in space. In the densest regions, this radiation can be absorbed and re-emitted by dust grains, creating a complex interplay between matter and energy. Dust grains, though they represent only about 1% of the interstellar medium by mass, play a crucial role in its evolution. These microscopic particles, smaller than the wavelength of visible light, absorb starlight and re-emit it in the infrared. They also serve as catalysts for chemical reactions, providing surfaces where hydrogen atoms can combine to form molecules. The motion of the interstellar medium follows the galaxy's rotation, but it's far from uniform. Gas flows from the outer regions toward the center, driven by spiral arm dynamics and gravitational torques. This inward flow provides the fuel for continued star formation in the galaxy's central regions, while also mixing material from different parts of the galaxy. Invisible to our eyes, but carrying enormous energy. Streams of subatomic particles race through the Triangulum galaxy at speeds approaching the ultimate cosmic speed limit. Cosmic rays are not rays at all, but individual atomic nuclei, mostly protons, and heavier atomic cores that have been accelerated to nearly the speed of light by the galaxy's most violent phenomena. These subatomic bullets carry energies millions of times greater than anything produced in terrestrial particle accelerators, making them the most energetic particles in the known universe. The most powerful cosmic rays possess energies equivalent to a baseball, thrown at 100 kilometers per hour, but concentrated into a single atomic nucleus smaller than a proton. When these ultra-high energy particles strike Earth's atmosphere, they create showers of secondary particles that can span kilometers and contain billions of individual particle interactions. The acceleration of cosmic rays to such extreme energies requires cosmic particle accelerators far more powerful than anything humans have built. Supernova shockwaves are the prime suspects, using magnetic fields and plasma physics to accelerate particles through a process called diffusive shock acceleration. As particles cross back and forth across the shock front, they gain energy with each crossing, eventually reaching speeds where relativistic effects become important. The strongest accelerators in the galaxy are the remnants of supernova explosions, expanding shells of hot gas that can maintain their acceleration capabilities for thousands of years. These cosmic machines can accelerate particles to energies exceeding 100 billion electron volts, creating a population of high-energy particles that fills the galaxy like an invisible fog. But supernovas are not the only source of cosmic rays. The galaxy's most massive stars produce powerful stellar winds that can accelerate particles to high energies. The collision regions where these winds meet the interstellar medium create shock waves that serve as natural particle accelerators. Even the galaxy's central regions, though lacking a supermassive black hole, may contain acceleration sites where magnetic field interactions can boost particle energies. The highest energy cosmic rays, those with energies exceeding 100 billion electron volts, pose a particular mystery. These particles carry so much energy that they should interact with the cosmic microwave background radiation, losing energy through a process called the GZK cutoff. This means they can only travel about 50 million light-years before losing their energy, suggesting they must originate from sources within our local group of galaxies. Cosmic rays don't travel in straight lines through the galaxy. Instead, they follow complex trajectories determined by the galaxy's magnetic field, which acts like an invisible maze for charged particles. The magnetic field can trap cosmic rays, bouncing them back and forth across the galaxy for millions of years before they finally escape into intergalactic space. This magnetic trapping has important consequences for the galaxy's evolution. Cosmic rays carry pressure that can influence the dynamics of the interstellar medium, potentially affecting star formation rates and the structure of molecular clouds. They also contribute to the heating of the interstellar gas, helping to maintain the warm phase of the interstellar medium that fills much of the galaxy's volume. The study of cosmic rays has revealed that the galaxy is a much more dynamic and energetic place than visible light observations might suggest. These high-energy particles carry information about the galaxy's most violent events, serving as messengers from regions where normal matter is heated to billions of degrees and magnetic fields reach strengths trillions of times stronger than Earth's magnetic field. When cosmic rays interact with the interstellar medium, they create secondary particles, including gamma rays, neutrinos, and antimatter. These secondary particles can be detected by space-based observatories, providing a window into cosmic ray interactions throughout the galaxy. The distribution of gamma rays across the sky reveals the locations of cosmic ray acceleration sites and the structure of the galactic magnetic field. Threading through every cubic centimeter of the Triangulum galaxy is an invisible scaffolding built from magnetic fields that shape the cosmos on the largest scales. The galaxy's magnetic field is roughly 1 million times weaker than Earth's magnetic field, so faint it would barely deflect a compass needle. Yet this tenuous field extends across tens of thousands of light years, creating a vast electromagnetic structure that influences everything from the birth of stars to the flow of cosmic rays. It's like a cosmic nervous system, an invisible network that connects distant regions of the galaxy through electromagnetic forces. This magnetic architecture follows the galaxy's spiral structure, with field lines that trace elegant curves through the galactic disk. The magnetic field is strongest in the spiral arms, where it's amplified by the compression of gas in these regions. It's weaker in the spaces between the arms, creating a complex three-dimensional pattern that mirrors the galaxy's visible structure. The magnetic field lines act like invisible highways for charged particles, channeling the flow of cosmic rays and hot plasma throughout the galaxy. Particles with electric charge become trapped along these field lines, spiraling around them in helical trajectories that can extend for thousands of light years. This creates a population of high-energy particles that fills the galaxy like an invisible atmosphere. The origin of galactic magnetic fields remains one of the great mysteries of astrophysics. Some theories suggest they were present from the galaxy's formation, remnants of primordial magnetic fields that existed in the early universe. Others propose that they were generated by dynamo processes, where the rotation of the galaxy amplifies weak seed fields over billions of years. The galactic dynamo operates like a cosmic generator, using the differential rotation of the galaxy to twist and amplify magnetic field lines. As the galaxy rotates, regions closer to the center move faster than those at the edge, stretching the magnetic field lines and increasing their strength. This process can amplify weak initial fields by factors of millions or billions over the galaxy's lifetime. The magnetic field also plays a crucial role in star formation, acting as both an enabler and an inhibitor of stellar birth. In molecular clouds, magnetic fields can support the gas against gravitational collapse, preventing stars from forming until the field is weakened or overcome by other forces. But magnetic fields can also channel the flow of gas, creating filamentary structures that serve as highways for material falling into star-forming regions. When stars do form, their births can disrupt the local magnetic field configuration. The powerful stellar winds from massive stars can drag magnetic field lines with them, creating complex magnetic structures around young stellar objects. These magnetic fields can help focus stellar winds into jets, creating the beautiful bipolar nebulae we observe around some young stars. The magnetic field also influences the galaxy's chemical evolution. Supernova explosions can create magnetic bubbles that trap heavy elements, preventing them from mixing with the broader interstellar medium. The magnetic field can also accelerate particles to high energies, creating cosmic rays that carry information about stellar explosions across vast distances. Recent observations have revealed that the magnetic field in the Triangulum galaxy is not uniform, but contains complex structures, including magnetic spirals, loops, and reversals. Some regions show evidence of magnetic field lines that have been twisted into helical configurations, possibly by the rotation of the galaxy or the influence of nearby galaxies. The interaction between the magnetic field and the interstellar medium creates a rich variety of plasma physics phenomena. Magnetic reconnection events can release enormous amounts of energy, heating gas to millions of degrees and accelerating particles to high energies. These processes may contribute to the heating of the interstellar medium and the acceleration of cosmic rays. The magnetic field also extends beyond the visible galaxy, creating a magnetosphere that may help protect the galaxy from intergalactic cosmic rays and other forms of high-energy radiation. This magnetic shield may be important for maintaining the galaxy's ability to form stars and support life over cosmic time. The Triangulum galaxy is performing an impossible dance, one that violates the fundamental laws of physics as we understand them. When astronomers measure how fast stars orbit the galactic center, they discover something that should not exist. According to Newton's laws of gravitation, stars farther from the center should move more slowly than those closer in, just like planets in our solar system. Mercury races around the sun at 47 kilometers per second, while distant Neptune crawls along at just 5 kilometers per second. This is the natural order of gravitational systems. But the Triangulum galaxy laughs at these rules. Stars throughout the galaxy's disk move at roughly the same speed, about 100 kilometers per second, regardless of their distance from the galactic center. Some regions even show stars accelerating as they get farther out, as if the galaxy's gravitational pull somehow increases with distance. It's like watching a merry-go-round where the horses on the outer edge gallop faster than those near the center. This flat rotation curve, as astronomers call it, represents one of the most profound puzzles in modern astrophysics. If we add up all the visible matter in the galaxy, every star and gas cloud we can detect, we get only about 10% of the mass needed to produce the observed rotation speeds. The remaining 90% is missing, hidden in some form of matter that doesn't interact with light. The implications are staggering. If the rotation curve is correct, then everything we can see in the galaxy, every bright star and glowing nebula, represents just the tip of an enormous iceberg. The bulk of the galaxy's mass is invisible, detectable only through its gravitational effects on the visible matter. 3 possibilities exist to explain this cosmic mystery. The first is that our understanding of gravity is fundamentally wrong. that Newton's and Einstein's theories break down on galactic scales. Some physicists have proposed modified theories of gravity that could explain the rotation curves without invoking invisible matter. But these theories struggle to explain other observations. The second possibility is that the galaxy contains vast amounts of ordinary matter that we simply cannot detect. This could include brown dwarfs, black holes, or dense molecular clouds too cold to emit detectable light. But detailed searches have failed to find enough of these objects to account for the missing mass. The third possibility is that the galaxy is embedded in a halo of exotic matter that interacts only through gravitational forces. This dark matter, as it's called, would outweigh all the visible matter in the galaxy by a factor of 5 to 1. Computer simulations show that such a dark matter halo could explain not only the rotation curve, but also the galaxy's stability over billions of years. The rotation curve also reveals the three-dimensional structure of the galaxy's mass distribution. The fact that the curve remains flat out to the galaxy's visible edge suggests that the dark matter halo extends far beyond the visible stars, possibly encompassing a volume hundreds of times larger than the luminous galaxy. We may be seeing only the bright core of a much larger, invisible structure. This dark matter halo would contain roughly 100 billion times the mass of our Sun, making it the dominant component of the galaxy's gravitational field. The visible stars and gas that create the galaxy's beautiful spiral structure would be mere passengers carried along by the gravity of this invisible ocean of exotic matter. The study of rotation curves in thousands of galaxies has revealed that this phenomenon is universal. Every spiral galaxy shows the same pattern, with rotation speeds that remain roughly constant or even increase with distance from the center. This suggests that dark matter is not a peculiarity of our local cosmic neighborhood, but a fundamental component of the universe. Hidden within the Triangulum galaxy's stellar populations are ancient witnesses to cosmic catastrophes that shaped the galaxy's violent past. Each generation of stars carries the chemical fingerprints of its birth environment, creating a stellar archaeology that reveals the galaxy's tumultuous history. The oldest stars, formed when the universe was young and pristine, contain almost no heavy elements. They're composed of nearly pure hydrogen and helium, the only elements forged in the Big Bang's nuclear furnace. These ancient stellar fossils tell a story of galactic cannibalism and merger violence. When astronomers analyze their chemical compositions, they find evidence that the Triangulum galaxy has devoured smaller companions throughout its history. Each merger event left its signature in the stellar populations, creating streams of stars with unusual chemical abundances and orbital patterns. The galaxy's stellar halo contains the most dramatic evidence of this violent past. Unlike the orderly rotation of disk stars, halo stars follow chaotic orbits that carry them far above and below the galactic plane. These stellar refugees are the survivors of galactic collisions, torn from their original homes and scattered into the galaxy's outer regions. Some halo stars move in retrograde orbits, traveling in the opposite direction to the galaxy's rotation. This backward motion is the smoking gun of galactic merger events, where the gravitational chaos of colliding galaxies can reverse stellar orbits and fling stars onto completely new trajectories. It's like finding cars driving backward on a highway, clear evidence of some past catastrophic event. The chemical abundances of stellar populations also reveal periods of enhanced star formation triggered by galactic interactions. When two galaxies collide, their gas reserves are compressed and stirred, triggering massive bursts of stellar birth. These starburst events create populations of stars with enhanced abundances of alpha elements like oxygen and magnesium, forged in the cores of massive stars that lived and died quickly during the chaotic merger. Different regions of the galaxy show distinct stellar populations, each telling part of the larger story. The galactic bulge contains older, more metal-poor stars that formed during the galaxy's earliest epochs. The disk populations show a gradient of chemical enrichment, with stars closer to the center generally containing more heavy elements than those in the outer regions. The spiral arms themselves create temporary stellar populations with characteristic ages and compositions. Stars born in the arms carry the chemical signatures of the compressed gas from which they formed, including enhanced abundances of elements produced by recent supernova explosions. As these stars age and drift away from their birth sites, they spread these chemical tracers throughout the galaxy. The most metal-rich stars in the galaxy are found in the youngest stellar populations, born from gas that has been enriched by billions of years of stellar evolution. These stars contain the full periodic table of elements, forged in successive generations of stellar cores and distributed by supernova explosions and stellar winds. By studying the ages, motions, and chemical compositions of millions of stars, astronomers can reconstruct the galaxy's merger history. Computer simulations suggest that the Triangulum galaxy has experienced at least several major merger events, each one adding new stellar populations and disrupting the galaxy's structure. The ongoing collision with the Andromeda galaxy, still billions of years in the future, will add another chapter to this stellar archaeological record. When future astronomers study the merged galaxy's stellar populations, they'll find evidence of our current epoch preserved in the chemical signatures and orbital patterns of the stars we see today. Deep within the Triangulum galaxy's spiral arms, colossal gas clouds are succumbing to the inexorable pull of their own gravity. In a cosmic ballet of collapse and creation, giant molecular clouds containing enough material to build millions of stars drift through space in a delicate balance between expansion and contraction. For millions of years, these clouds can remain stable, their internal pressure from random molecular motions perfectly balancing the inward pull of gravity. But this equilibrium is precarious, like a boulder balanced on a cliff edge, waiting for the slightest disturbance to trigger catastrophic change. The trigger often comes from outside the cloud itself. A shockwave from a nearby supernova explosion, the gravitational influence of a passing star, or the compression caused by spiral arm dynamics can tip the balance. Once gravity gains the upper hand, the collapse becomes inevitable, governed by the same physics that created our solar system 4.5 billion years ago. The collapse begins slowly, almost imperceptibly. The cloud contracts by just a few percent over thousands of years, gradually increasing its density while cooling toward absolute zero. But as the cloud becomes denser, its gravitational pull strengthens, accelerating the infall of material. What started as a gentle drift becomes a headlong plunge toward the center. As the gas compresses, it begins to fragment into smaller clumps, each destined to become a stellar nursery. The largest fragments may contain hundreds of times the mass of our Sun, while the smallest might have just enough material to form a single star. This fragmentation process is chaotic and unpredictable, governed by turbulence, magnetic fields, and the random motions of the gas itself. The collapsing fragments heat up as gravitational potential energy is converted to thermal energy, following the same principle that makes a bicycle pump warm when you compress air. Temperatures that started near absolute zero climb to hundreds, then thousands of degrees. The gas begins to glow faintly in infrared light, marking the birth of what astronomers call protostars. But gravity's work is far from finished. As the protostar continues to contract, its core temperature climbs toward the 10 million degrees needed to ignite nuclear fusion. The journey from a cold molecular cloud to a burning star takes about 50 million years for a sun-like star, but can happen much faster for more massive objects. The most massive protostars can ignite fusion in less than 1 million years, racing through their formation process like cosmic sprinters. The collapse isn't uniform or smooth. Magnetic fields threading through the gas can slow the infall, while rotation causes the material to flatten into a disk around the growing protostar. This disk becomes the birthplace of planetary systems, where dust grains stick together to form pebbles, then boulders, then planets. The same gravitational collapse that creates stars also sets the stage for the formation of worlds. Some collapsing clouds create not single stars, but entire stellar systems. Multiple fragmentations can produce binary and triple star systems, where two or more stars orbit their common center of mass. In the densest regions, dozens or even hundreds of stars can form simultaneously, creating the open clusters that pepper the galaxy's spiral arms. The process of gravitational collapse operates on many scales throughout the galaxy. Individual stars form from the collapse of small gas clumps, but entire galaxies were created by the gravitational collapse of even larger structures in the early universe. The same fundamental physics governs the formation of planetary systems, star clusters, and the cosmic web of dark matter that scaffolds the universe. Computer simulations reveal that gravitational collapse is a hierarchical process, with smaller structures forming first and then assembling into larger ones. This bottom-up construction explains why we see such a rich variety of astronomical objects, from asteroids to galaxy clusters, all shaped by the same fundamental force. Across the Triangulum galaxy, the violent deaths of massive stars are triggering avalanches of stellar birth in a cosmic cycle, where destruction enables creation. When a massive star explodes as a supernova, it doesn't simply disappear in a flash of light. The explosion creates a shockwave that races through space at speeds exceeding 10,000 kilometers per second, carrying the energy equivalent of our sun's entire lifetime output compressed into a few seconds. This expanding shell of superheated gas becomes a cosmic bulldozer, reshaping the galaxy's architecture and seeding the next generation of stars. The shockwave begins its journey when the star's core collapses and rebounds, sending a pressure pulse racing through the stellar envelope. Within hours, this wave breaks free from the dying star and plows into the surrounding interstellar medium. The collision creates temperatures exceeding 100 million degrees, hot enough to strip electrons from atoms and create a plasma so energetic it glows in X-rays. As the shockwave expands, it encounters the giant molecular clouds that drift through the galaxy's spiral arms. These clouds, which have existed in a stable equilibrium for millions of years, suddenly find themselves under assault by a wall of superheated gas traveling faster than a speeding bullet. The gentle balance between gravity and pressure that kept them stable is shattered in an instant. The shockwave doesn't destroy these clouds, but compresses them like a cosmic fist squeezing a sponge. The compression increases the cloud's density by factors of 10 or more, strengthening gravity's grip and triggering the gravitational collapse that leads to star formation. Regions that might have remained stable for millions more years suddenly begin their transformation into stellar nurseries. This process, called triggered star formation, can create spectacular bursts of stellar birth across vast regions of the galaxy. A single supernova can influence star formation over areas spanning hundreds of light years, potentially triggering the birth of thousands of new stars. These stellar babies will shine for millions or billions of years, carrying forward the legacy of the star that died to enable their creation. The shock waves don't just compress existing clouds, but also collect material from the diffuse interstellar medium, sweeping it up like cosmic snowplows. This collected material can form new molecular clouds in regions where none existed before, expanding the galaxy's star-forming capacity and spreading stellar birth into previously barren areas. The heavy elements dispersed by the supernova explosion also enrich the triggered star formation. The shockwave carries carbon, oxygen, silicon, and iron forged in the dying star's core, mixing these elements with the hydrogen and helium of the molecular clouds. The new stars that form will have higher abundances of heavy elements than their predecessors, enabling them to form rocky planets and potentially support the chemistry of life. Sequential star formation can create chains of stellar birth across the galaxy. When the first generation of triggered stars includes massive ones, they too will eventually explode as supernovas, creating new shockwaves that can trigger even more star formation. This creates a propagating wave of stellar birth that can travel across entire spiral arms over tens of millions of years. The process is beautifully visible in the galaxy's star-forming regions, where we can see multiple generations of stars at different evolutionary stages. Young, hot, blue stars mark the locations of recent shock-triggered star formation, while older, red stars show where previous episodes occurred. The spatial arrangement of these stellar populations reveals the history of supernova-driven star formation across the region. Some of the galaxy's most spectacular stellar nurseries owe their existence to this process. The massive star-forming complexes that dominate the spiral arms often show evidence of triggered formation, with expanding bubbles of hot gas surrounding groups of young, massive stars. These regions will eventually produce their own supernovas, continuing the cycle of death and birth that has operated throughout the galaxy's history. Beyond the furthest visible stars of the Triangulum galaxy lies a vast empire of dark matter that extends 10 times farther than the light can reach, creating a cosmic structure larger than anything our eyes can perceive. The bright spiral arms and glowing star-forming regions that define our view of the galaxy represent only the luminous heart of a much larger gravitational system. Surrounding this visible disk is a roughly spherical halo of dark matter that contains 5 times more mass than all the visible stars combined. If we could see this invisible structure, the galaxy would appear as a vast, diffuse sphere rather than the elegant spiral we observe. This dark matter halo extends to distances of nearly 1 million light-years from the galactic center, making the true galaxy 15 times larger in diameter than its visible appearance suggests. The halo's outer boundary is so far from the galactic center that light from the galaxy's core takes 1 million years to reach its edge, longer than humans have existed as a species. The halo's gravitational influence shapes everything within it. The beautiful spiral structure we see exists only because the dark matter halo provides the gravitational scaffolding needed to maintain it. Without this invisible foundation, the galaxy's rotation would have wound up the spiral arms long ago, destroying the elegant pattern we observe today. Computer simulations reveal that the dark matter halo has a complex internal structure with subhalos and density variations that reflect the galaxy's violent formation history. These substructures are the gravitational fossils of smaller dark matter clumps that merged to build the galaxy, each one adding its mass to the growing halo over billions of years. The halo also contains more than just dark matter. Scattered throughout this vast volume are ancient globular clusters, stellar streams from disrupted dwarf galaxies, and a diffuse population of halo stars that follow highly elliptical orbits. These objects serve as tracers of the halo's gravitational field, revealing its 3-dimensional structure through their motions, Hot gas with temperatures exceeding 1 million degrees fills portions of the halo, creating a tenuous atmosphere around the galaxy. This gas is so hot and diffuse, it's invisible to optical telescopes, but can be detected through its X-ray emission. The hot halo may contain as much mass as all the stars in the galaxy, representing a significant reservoir of baryonic matter hidden in the galaxy's outskirts. The boundary between the galaxy's halo and intergalactic space is not sharp, but gradual, fading slowly into the cosmic web of dark matter that connects all galaxies. This transition region, called the galaxy's virial radius, marks the approximate limit of the galaxy's gravitational influence and defines the edge of its dark matter halo. Within this vast halo, smaller satellite galaxies orbit like planets around a star. These dwarf companions are embedded in their own dark matter subhalos, creating a hierarchical structure where halos exist within larger halos. The orbital motions of these satellites provide crucial information about the total mass and distribution of dark matter within the halo. The halo's rotation is much slower than that of the visible disk, creating a situation where the luminous galaxy spins within its dark matter envelope like a wheel within a wheel. This differential rotation may help explain some of the galaxy's observed properties, including the persistence of its spiral structure over cosmic time. Recent observations have detected streams of hydrogen gas extending far into the halo, possibly representing the remnants of gas accretion events that helped build the galaxy. These gas streams may be the visible traces of the cosmic web filaments that channel matter from intergalactic space into the galaxy's gravitational well. The Triangulum galaxy is being slowly torn apart by invisible forces. Its outer regions stretched and warped by the gravitational influence of its massive neighbor, the Andromeda Galaxy. Tidal forces, the same phenomenon that creates ocean tides on Earth, operate on galactic scales with devastating effect. The side of Triangulum closest to Andromeda experiences a stronger gravitational pull than the side farther away, creating a differential force that stretches the galaxy like cosmic taffy. This gentle but relentless stretching has been operating for billions of years, gradually reshaping the galaxy's structure. The effects are most visible in the galaxy's outer regions, where the gravitational grip is weakest. Streams of stars and gas are being pulled away from the galaxy's edges, creating tidal tails that extend far into intergalactic space. These stellar streams mark the path of Triangulum's orbit around Andromeda like breadcrumbs dropped by a cosmic wanderer. Computer simulations reveal that Triangulum has lost a significant fraction of its original mass to tidal stripping. Stars that once belonged to the galaxy now drift in the space between galaxies, gravitationally unbound and destined to spend eternity in the cosmic void. This ongoing mass loss is gradually reducing the galaxy's size and altering its internal dynamics. The tidal forces don't affect all parts of the galaxy equally. The central regions, where stars are more tightly bound by the galaxy's gravity, remain relatively intact. But the outer spiral arms show clear signs of distortion, with asymmetries and warping that reflect the external gravitational influence. The galaxy's once perfect spiral structure is being gradually unwound by these external forces. The interaction between Triangulum and Andromeda is not a simple two-body problem, but involves the complex gravitational dance of three major galaxies. Our own Milky Way also exerts a significant gravitational influence, creating a three-way tug-of-war that makes the system's evolution difficult to predict. The competing gravitational fields create resonances and instabilities that can dramatically alter orbital trajectories. Recent observations have detected a bridge of hydrogen gas connecting Triangulum to Andromeda, evidence of direct material transfer between the two galaxies. This gaseous umbilical cord represents matter being stripped from Triangulum and captured by its larger neighbor. A slow-motion cosmic cannibalism that will eventually consume the smaller galaxy entirely. The tidal interaction also affects star formation within Triangulum. The compression and stretching of gas clouds by tidal forces can trigger new episodes of stellar birth in some regions while suppressing it in others. This creates a complex pattern of star formation that varies across the galaxy, with some spiral arms showing enhanced activity while others appear depleted. The galaxy's dark matter halo is also being stripped by tidal forces. Though this invisible mass loss is harder to detect directly, computer models suggest that Triangulum may have lost half or more of its original dark matter halo to tidal stripping, fundamentally altering its gravitational structure and internal dynamics. As Triangulum orbits Andromeda, it experiences varying tidal forces depending on its distance from the larger galaxy. At the closest approach of its elliptical orbit, the tidal forces intensify, accelerating the stripping process and potentially triggering bursts of star formation. During more distant phases, the galaxy can partially recover, reforming some of its disrupted structure. The tidal interaction is gradually circularizing Triangulum's orbit, causing it to spiral inward toward an eventual merger with Andromeda. This process will accelerate as the galaxy loses mass and orbital energy to tidal friction, leading to an increasingly rapid decay of its orbit. The galaxy is essentially falling toward its doom, though the process will take billions of years to complete. Deep within the cosmic machinery of the Triangulum galaxy pulses a rhythm that astronomers are only beginning to understand. A cycle of stellar birth and death that follows mysterious patterns spanning millions of years. Star formation in the galaxy is not constant, but varies dramatically over time, like a cosmic heartbeat that speeds up and slows down according to some hidden conductor. During peak periods, the galaxy can produce new stars at rates 10 times higher than average, filling the spiral arms with brilliant blue giants and glowing nebulae. During quiet periods, star formation nearly ceases, leaving only the fading embers of previous stellar generations. These cycles operate on multiple timescales simultaneously. Short-term variations occur over millions of years, possibly triggered by the galaxy's passage through spiral arms or interactions with gas clouds. Longer cycles span hundreds of millions of years, potentially linked to the galaxy's orbital motion around Andromeda or encounters with other members of the local group. The triggers for these star formation cycles remain largely mysterious. One possibility is that spiral density waves create periodic compressions of the interstellar medium, squeezing gas clouds until they collapse to form stars. As the galaxy rotates, different regions pass through these compression zones, creating waves of star formation that sweep around the galactic disk like cosmic wildfire. Another potential driver is the galaxy's interaction with the cosmic web of dark matter and gas that permeates the universe. As the galaxy moves through this large-scale structure, it may encounter filaments of gas that trigger bursts of star formation when they fall into the galactic disk. These cosmic rain showers could explain some of the observed variations in star formation rates. The galaxy's magnetic field may also play a role in regulating star formation cycles. Magnetic fields can support gas clouds against gravitational collapse, preventing star formation until the field is weakened by turbulence or reconnection events. The buildup and release of magnetic pressure could create oscillating patterns of star formation across the galaxy. Internal feedback mechanisms add another layer of complexity to these cycles. Massive stars formed during intense star formation episodes produce powerful stellar winds and eventually explode as supernovas, heating the surrounding gas and potentially suppressing further star formation. This negative feedback can create boom and bust cycles, where periods of intense activity are followed by relative quiescence. The chemical evolution of the galaxy also influences star formation cycles. As successive generations of stars enrich the interstellar medium with heavy elements, they change the cooling properties of the gas and the efficiency of star formation. Regions with higher metallicity may form stars more easily, while metal-poor regions may require stronger triggers to initiate collapse. Climate change on galactic scales may drive some of the longest star formation cycles. The galaxy's overall temperature and pressure can vary over cosmic time, influenced by factors such as the cosmic background radiation, the density of the local group, and the galaxy's interaction history. These changes can alter the conditions for star formation throughout the galaxy. Recent observations have revealed that star formation in Triangulum shows correlations with activity in nearby galaxies, suggesting that environmental factors operating on scales much larger than individual galaxies may influence stellar birth rates. The local group as a whole may experience coordinated cycles of star formation driven by external influences. The study of star formation histories in different regions of the galaxy reveals that these cycles are not uniform, but vary from place to place. The inner regions show different patterns than the outer disk, and some spiral arms appear more active than others. This spatial variation suggests that multiple mechanisms may be operating simultaneously. In the nuclear furnaces of dying stars throughout the Triangulum galaxy, cosmic alchemists are forging the elements that will one day become planets, life forms, and perhaps even consciousness itself. When the universe began, only the three lightest elements existed: hydrogen, helium, and trace amounts of lithium. Everything else, every atom of carbon in our DNA, every molecule of oxygen we breathe, every grain of silicon in a planetary crust had to be created in the hearts of stars through nuclear fusion. The galaxy has spent 13 billion years slowly building up the periodic table, one stellar death at a time. The stellar nucleosynthesis process operates like a cosmic factory with multiple production lines. In the cores of main sequence stars like our Sun, hydrogen fuses to form helium through the proton-proton chain, releasing the energy that makes stars shine. But when these stars exhaust their hydrogen fuel, they begin burning helium to create carbon and oxygen in a process called the triple alpha reaction. More massive stars can reach higher temperatures and pressures in their cores, enabling them to forge heavier elements through successive burning stages. They burn carbon to create neon and magnesium, oxygen to create silicon and sulfur, and finally, silicon to create iron peak elements. Each burning stage operates at progressively higher temperatures, reaching over 3 billion degrees in the final silicon burning phase. But stellar cores cannot create elements heavier than iron through normal fusion. These elements require the extreme conditions found only in supernova explosions, where neutron capture processes can build up heavy nuclei in seconds. The rapid neutron capture process, called the R process, creates roughly half of all elements heavier than iron, including gold, platinum, and uranium. The slow neutron capture process, called the S process, operates in the extended atmospheres of dying giant stars, gradually building up elements like strontium, barium, and lead over thousands of years. This process creates the other half of heavy elements, adding them to the stellar wind that carries material away from the dying star. The most recent addition to our understanding of stellar nucleosynthesis comes from the detection of neutron star mergers, which create kilonova explosions that forge the heaviest elements through rapid neutron capture. These rare but violent events may be responsible for creating most of the gold and platinum in the universe, including the precious metals found on Earth. Each stellar generation adds to the galaxy's chemical inventory, gradually enriching the interstellar medium with heavier elements. The first stars were composed almost entirely of hydrogen and helium, but subsequent generations incorporated the heavy elements produced by their predecessors. This process of chemical evolution has continued for billions of years, steadily increasing the galaxy's metallicity. The distribution of heavy elements throughout the galaxy reflects its star formation history. The central regions, where star formation has been most active, show the highest abundances of heavy elements. The outer regions, where fewer generations of stars have lived and died, remain more pristine, with compositions closer to the primordial hydrogen and helium. This chemical evolution has profound implications for planet formation and the potential for life. Rocky planets like Earth can only form from material enriched with heavy elements produced by previous stellar generations. The first generation of stars could not have formed planetary systems like ours because the necessary elements simply didn't exist yet. The galaxy's increasing metallicity also affects star formation itself. Heavy elements serve as coolants in molecular clouds, allowing them to radiate away thermal energy and collapse more efficiently. Higher metallicity gas can form stars more easily, but it also tends to produce more low-mass stars relative to high-mass ones, affecting the galaxy's overall evolution. From the Triangulum galaxy's star-forming regions rise invisible fountains of superheated gas, carrying the galaxy's lifeblood into the cosmic void in a process that may ultimately determine its fate. Galactic winds are among the most powerful forces shaping galaxy evolution, yet they're almost entirely invisible to the naked eye. These cosmic hurricanes consist of gas heated to millions of degrees by stellar winds, supernova explosions, and shock waves from star formation. The hot gas expands rapidly, breaking free from the galaxy's gravitational grip and flowing into intergalactic space at speeds exceeding 1,000 kilometers per second. The process begins in the galaxy's most active star-forming regions, where massive stars burn through their fuel at prodigious rates. Their powerful stellar winds, moving at speeds up to 3,000 kilometers per second, collide and create superbubbles of hot gas that can grow to hundreds of light years in diameter. When these bubbles break through the galactic disk, they create chimneys that channel hot gas into the galaxy's halo. Supernova explosions add enormous amounts of energy to these outflows, heating gas to temperatures exceeding 10 million degrees and accelerating it to escape velocity. A single supernova can inject as much energy into the interstellar medium as our Sun will produce in its entire 10 billion-year lifetime. In regions where multiple supernovas occur in quick succession, the combined energy can blow vast cavities in the galactic disk. These galactic winds don't just carry away mass and energy, but also transport the heavy elements forged in stellar cores. Carbon, oxygen, silicon, and iron produced by nuclear fusion are swept up in the outflows and carried into intergalactic space, where they can enrich the cosmic web and potentially seed future galaxy formation. This process represents a form of galactic pollution, contaminating the pristine hydrogen and helium of the early universe. The mass loss rate from galactic winds can be substantial, with some galaxies losing material faster than they form new stars. For the Triangulum galaxy, computer simulations suggest that galactic winds may be removing several solar masses of material every year, gradually depleting the galaxy's gas reservoirs and reducing its future star formation potential. The winds don't escape uniformly, but follow preferred directions determined by the galaxy's structure and magnetic field. Gas tends to flow more easily perpendicular to the galactic disk, where the gravitational potential is lowest. This creates bipolar outflows that can extend thousands of light years above and below the galactic plane, forming a cosmic hourglass shape around the galaxy. The magnetic field plays a crucial role in shaping these outflows. channeling the flow of charged particles and creating complex structures within the wind. Magnetic field lines can act like cosmic highways for the escaping gas, while magnetic pressure can help accelerate the outflow and prevent it from falling back onto the galaxy. Some of the escaping gas may eventually return to the galaxy through a process called galactic recycling. Gas blown into the halo can cool and condense, eventually falling back onto the galactic disk, where it can fuel new star formation. This creates a galactic fountain effect, where material cycles between the disks, say the disk and halo, over hundreds of millions of years. The interaction between galactic winds and the surrounding intergalactic medium creates shock waves and turbulence that can be detected by space telescopes. These observations reveal that galactic winds are not smooth, steady flows but turbulent, chaotic phenomena with complex internal structures and time-varying properties. Different types of galaxies produce different kinds of winds. Massive galaxies with active star formation can generate powerful outflows that clear their central regions of gas, potentially quenching further star formation. Smaller galaxies like Triangulum may have weaker winds that escape more gradually, allowing continued star formation over longer timescales. In approximately 4 billion years, the Triangulum galaxy will participate in the most spectacular collision in the local group's history. A three-way galactic merger that will forever transform our corner of the universe. The collision began billions of years ago with the first gravitational stirrings between the Andromeda Galaxy and our own Milky Way. These two spiral giants have been approaching each other for most of cosmic history, their mutual gravitational attraction overcoming the expansion of the universe and drawing them together in an inexorable dance of destruction and creation. Current measurements show Andromeda approaching at over 100 kilometers per second, closing the gap between the galaxies by the width of Earth's orbit every year. This may seem slow by cosmic standards, but on the timescales of galactic evolution, it represents a headlong collision course that cannot be avoided. The merger will arrive faster than the sun will exhaust its fuel, making it a certainty for any civilizations that might witness it. The Triangulum galaxy finds itself caught in the middle of this cosmic catastrophe as the third largest galaxy in the local group. It lacks the mass to significantly alter the collision between its larger neighbors, but its fate is inextricably linked to theirs. Computer simulations suggest multiple possible outcomes for Triangulum, ranging from complete destruction to survival as a satellite of the merged galaxy. The collision will not be a gentle affair. When galaxies merge, their gravitational fields interact chaotically, flinging stars into new orbits and triggering massive bursts of star formation as gas clouds collide and compress. The elegant spiral structures that define all three galaxies will be completely destroyed, their stars scattered into a new elliptical galaxy that astronomers have already nicknamed Milkomeda. For the Triangulum galaxy, the collision represents an existential threat. Its relatively small mass makes it vulnerable to tidal disruption by the larger galaxies. Streams of stars may be torn from its outer regions and scattered throughout the merger zone, while its central core could be either destroyed or captured as a satellite of the final merged galaxy. The timing of Triangulum's involvement in the collision depends on its complex orbital motion around Andromeda. If it completes another orbit before the main collision occurs, it might escape the initial chaos, only to be drawn into the merger later. If it approaches during the peak of the collision, it could be completely disrupted by the gravitational turmoil. The stellar populations of all three galaxies will be thoroughly mixed during the merger, creating a new galaxy with a complex stellar archaeology. Stars from Triangulum will find themselves orbiting alongside stars from the Milky Way and Andromeda, their original galactic identities erased by the cosmic blender of gravitational dynamics. The The supermassive black holes at the centers of the merging galaxies will eventually spiral together and merge, creating gravitational waves that will ripple across the universe. This black hole merger will be one of the most energetic events in the local group's history, releasing more energy and gravitational waves than all the stars in the merged galaxy combined. The merger will also trigger the final burst of star formation in the region as the collision compresses gas clouds and triggers gravitational collapse across vast areas. This starburst phase could make the merged galaxy one of the brightest objects in the local universe for a brief period, before the gas reserves are exhausted and star formation ceases. For any planetary systems in the region, the merger will be a time of cosmic upheaval. While direct stellar collisions will be rare due to the vast distances between stars, the changing gravitational fields could disrupt planetary orbits and send worlds into new, potentially uninhabitable trajectories. Some planets might be flung into interstellar space, while others could find themselves orbiting different stars entirely. The remnant of this cosmic collision will be a massive elliptical galaxy, roughly twice the size of the current Milky Way, but with a very different character. The new galaxy will have consumed most of the gas in the local group, leaving little material for future star formation. It will gradually fade as its stars age and die, eventually becoming a galactic graveyard of white dwarfs and stellar remnants. Orbiting the Triangulum galaxy like planetary moons around a giant world are dozens of smaller galaxies, cosmic satellites that form a miniature kingdom in the vast darkness of intergalactic space. These dwarf galaxies are the Triangulum galaxy's gravitational subjects, bound by invisible chains of dark matter and destined to follow elliptical orbits that carry them through the galaxy's extended halo. Each satellite is a galaxy in its own right, containing millions to billions of stars, but their fates are controlled by their massive overlord's gravitational influence. The largest of these cosmic companions shine with the light of hundreds of millions of stars, making them visible as faint smudges of light, even from great distances. But most of Triangulum's satellites are dwarf spheroidal galaxies, so faint they were only discovered when advanced telescopes began systematically surveying the galaxy's surroundings. These galactic pygmies contain more dark matter than visible stars, making them some of the most dark matter-dominated objects in the universe. The satellite system around Triangulum tells a story of cosmic hierarchy and gravitational dominance. Computer simulations predict that every large galaxy should be surrounded by hundreds of smaller dark matter halos. But only a fraction of these halos contain enough ordinary matter to form visible stars. The satellites we can observe represent the tip of an iceberg of invisible dark matter substructure. Each satellite galaxy follows its own unique orbital path, some taking hundreds of millions of years to complete a single revolution around Triangulum. The closest satellites experience strong tidal forces that can strip away their outer stars, creating stellar streams that trace their orbital paths like cosmic breadcrumbs. These tidal streams provide direct evidence of the ongoing gravitational interaction between the satellites and their host galaxy. The satellite galaxies are not passive objects, but active participants in the galaxy's evolution. As they orbit through Triangulum's halo, they can trigger gravitational resonances that affect the host galaxy's structure. Their gravitational influence can heat the galactic disk, thicken spiral arms, and potentially influence star formation rates in different regions. Some satellites are gradually being consumed by their host galaxy through tidal disruption. Over billions of years, repeated passages through the galaxy's gravitational field strip away their stars, eventually leaving only their central dark matter cores. The disrupted stellar material becomes part of the galaxy's extended halo, adding to its stellar population and altering its chemical composition. The diversity of satellite galaxies around Triangulum reflects different formation histories and environments. Some formed early in cosmic history when gas densities were higher, creating relatively metal-rich stellar populations. Others formed more recently from gas that had been previously heated and ionized, resulting in smaller, more metal-poor systems. Star formation in satellite galaxies is often suppressed by environmental effects. The hot halo gas around Triangulum can strip away the cool gas needed for star formation through a process called ram pressure stripping. Additionally, the galaxy's ultraviolet radiation can ionize and heat gas in nearby satellites, preventing it from cooling and collapsing to form new stars. The study of satellite galaxies has revealed important constraints on dark matter physics. The number, distribution, and properties of satellites depend on the nature of dark matter particles and the way structure forms in the universe. Comparing observations with computer simulations helps test different dark matter models and refine our understanding of cosmic evolution. Invisible to our eyes, but detectable by the most sensitive instruments ever built. Gravitational waves are constantly washing through the Triangulum galaxy, carrying messages from some of the most violent events in cosmic history. These ripples in space-time itself are created when massive objects accelerate through the universe's gravitational field. Every orbiting binary star system, every colliding black hole, every exploding supernova sends gravitational waves racing across the cosmos at the speed of light. The galaxy exists within an ocean of these space-time distortions, each wave carrying information about distant cosmic catastrophes. The most powerful gravitational wave sources are the mergers of compact objects like neutron stars and black holes. When two neutron stars spiral together and collide, they create gravitational waves so strong they can be detected from billions of light years away. These cosmic crashes occur perhaps once every few 100,000 years in a galaxy like Triangulum. But the waves they produce ripple outward for eternity. The waves themselves represent a fundamental prediction of Einstein's general relativity, the stretching and compression of space and time by accelerating masses. As a gravitational wave passes through the galaxy, it alternately stretches and compresses distances by amounts smaller than 1,000th the width of a proton. This incredibly tiny effect can only be detected by laser interferometry experiments that measure changes in the length of kilometer-scale baselines. The discovery of gravitational waves has opened an entirely new window onto the universe, allowing astronomers to detect events that produce no light at all. Binary black hole mergers, which were previously invisible to traditional telescopes, now announce themselves through the characteristic chirp of gravitational waves as the orbiting objects spiral together faster and faster before the final collision. Within the Triangulum galaxy, dozens of known binary systems are slowly losing energy to gravitational wave emission, causing their orbits to decay over millions of years. The most famous example is a binary pulsar system where one neutron star acts as a cosmic lighthouse, sweeping beams of radio waves across space with clockwork precision. The gradual speedup of this orbital dance matches Einstein's predictions exactly. The galaxy's supermassive black hole mergers, which occurred during its formation billions of years ago, would have created some of the most powerful gravitational wave events in cosmic history. These early mergers helped shape the galaxy's central structure and may have ejected smaller black holes through gravitational recoil effects, creating the population of wandering black holes that roam the galaxy today. Gravitational waves also carry information about the expansion history of the universe. By measuring both the wave amplitude and the redshift of their sources, astronomers can determine cosmic distances without relying on traditional distance indicators. This makes gravitational wave astronomy a powerful tool for studying dark energy and the acceleration of cosmic expansion. The waves propagate through matter almost unimpeded, passing through stars, planets, and entire galaxies as if they weren't there. This means that gravitational wave signals preserve information about their sources with extraordinary fidelity, providing clean measurements of masses, spins, and orbital parameters that would be impossible to obtain through electromagnetic observations alone. Future space-based gravitational wave detectors will be sensitive to lower frequency waves produced by massive black hole mergers and galactic binary systems. These instruments will be able to detect every white dwarf binary in the Milky Way and track the population of massive black hole pairs throughout the observable universe. The constant bombardment of gravitational waves may also have subtle effects on the galaxy's structure and evolution, while individual waves are extremely weak. The cumulative effect of billions of years of gravitational wave radiation may influence the dynamics of stellar systems and the evolution of binary populations. Every photon of light from the Triangulum galaxy carries within it a timestamp from the past, creating a cosmic archaeological record that allows us to witness the galaxy's evolution across billions of years of cosmic history. Light takes time to travel through space, turning every astronomical observation into a journey back in time. The light from Triangulum's core that reaches us tonight began its journey 3 million years ago, when early humans were first walking upright on Earth. More distant regions of the galaxy show us even earlier epochs, creating a time machine that reveals how the galaxy has changed over cosmic history. The galaxy's oldest stars preserve information from the universe's youth, when heavy elements were scarce and star formation proceeded under very different conditions than today. These ancient stellar populations contain the chemical signatures from the first generation of massive stars, which lived fast, died young, and enriched the early universe with the first heavy elements beyond hydrogen and helium. By studying stars of different ages throughout the galaxy, astronomers can reconstruct its star formation history, tracing periods of intense stellar birth triggered by galactic mergers or gas infall events. The chemical abundances of these stellar populations reveal how the galaxy gradually enriched itself with heavy elements over billions of years of stellar evolution. The most distant galaxies visible to our telescopes show us cosmic conditions from over 13 billion years ago, when the universe was less than 1 billion years old. These early galaxies were smaller, more irregular, and had higher rates of star formation than modern spiral galaxies like Triangulum. They represent the building blocks from which today's massive galaxies were assembled through mergers and accretion. The Hubble Space Telescope and other deep field observations have revealed that the early universe was filled with small, star-forming galaxies that gradually merged to form larger systems. The Triangulum galaxy likely formed through the merger of dozens of these early galaxy fragments, each contributing its stars and gas to the growing system. Ancient light also reveals periods when the galaxy experienced major disruptions. Stellar streams and tidal tails preserve evidence of past galactic encounters, their stars carrying chemical signatures and kinematic information that reveals when and how these interactions occurred. Some of these disrupted systems may be the remnants of satellite galaxies that were completely torn apart by tidal forces. The galaxy's globular clusters serve as stellar time capsules, preserving populations of stars that formed during specific epochs in galactic history. The ages and chemical compositions of these clusters reveal periods of intense star formation that may have been triggered by major merger events or episodes of gas accretion from the cosmic web. Even the galaxy's dark matter halo contains information about its formation history. Computer simulations suggest that the halo formed through the gradual accumulation of smaller dark matter clumps, each leaving subtle signatures in the halo's density profile and substructure. These dark matter fossils can be detected through their gravitational effects on stellar streams and satellite galaxies. The cosmic microwave background radiation provides a snapshot of the universe when it was only 380,000 years old. long before the first stars formed. Tiny temperature fluctuations in this ancient light reveal the density variations that eventually grew into galaxies, like Triangulum, through gravitational amplification over cosmic time. Observations of quasars and other distant active galactic nuclei show us how supermassive black holes grew and influenced galaxy evolution in the early universe. The Triangulum galaxy's lack of a central supermassive black hole suggests it may have had a different evolutionary history than galaxies that experienced more violent growth phases. Surrounding the Triangulum galaxy and permeating every cubic centimeter of space is a mysterious force that is tearing the universe apart, accelerating the expansion of space itself and driving galaxies away from each other at ever-increasing speeds. Dark energy represents the most profound mystery in modern cosmology. An unknown form of energy that makes up roughly 70% of the universe, but whose nature remains completely enigmatic. Unlike dark matter, which clumps together gravitationally, dark energy appears to be smoothly distributed throughout space, exerting a constant pressure that acts like anti-gravity on cosmic scales. The discovery of cosmic acceleration came from observations of distant supernovas, stellar explosions so consistent in their brightness that they serve as cosmic standard candles. When astronomers measured the distances to these exploding stars, they found that the most distant ones appeared fainter than expected, indicating that the expansion of the universe has been speeding up over the past several billion years. This acceleration defies our intuitive understanding of gravity and cosmic evolution. After the Big Bang, the mutual gravitational attraction of all matter in the universe should have gradually slowed the expansion, possibly even reversing it in a cosmic collapse. Instead, the expansion began accelerating roughly 5 billion years ago, when dark energy's influence overcame the gravitational pull of matter. For galaxies within the local group, including Triangulum, dark energy's effects are currently negligible compared to their mutual gravitational attraction. The local group remains gravitationally bound and will continue to evolve through mergers and interactions regardless of cosmic acceleration. But on larger scales, dark energy is already having dramatic effects on the universe's structure. Galaxy clusters beyond the local group are being carried apart by cosmic expansion faster than light can travel between them. In the far future, these distant galaxies will disappear beyond our cosmic horizon, their light redshifted to such long wavelengths that they become effectively invisible. The observable universe will gradually shrink to include only the local group and its immediate neighbors. The nature of dark energy remains one of the greatest unsolved problems in physics. One possibility is that it represents the energy of empty space itself, a quantum phenomenon called vacuum energy. But calculations of vacuum energy from particle physics predict values that are vastly larger than what we observe, creating a discrepancy of more than 100 orders of magnitude. Another possibility is that dark energy is a dynamic field that changes over time, similar to the inflaton field thought to have driven cosmic inflation in the early universe. This quintessence field could have different properties at different times, potentially explaining why dark energy only began to dominate the universe relatively recently in cosmic history. Some theories propose modifications to Einstein's general relativity that could explain cosmic acceleration without invoking dark energy. These modified gravity theories suggest that gravity behaves differently on cosmic scales than it does in the solar system, creating an apparent acceleration without requiring a new form of energy. The future evolution of dark energy will determine the ultimate fate of the universe. If dark energy remains constant, the universe will continue expanding forever, gradually cooling and diluting until all the stars burn out and only black holes remain. If dark energy increases over time, It could eventually overcome all other forces, tearing apart galaxies, stars, and even atoms in a cosmic event called the Big Rip. Measurements of cosmic acceleration using different techniques all point to the same conclusion. The universe's expansion is speeding up, driven by some form of energy that permeates all of space. Observations of galaxy clusters, gravitational lensing, and the cosmic microwave background all provide independent confirmation of dark energy's existence. The local group's isolation in an accelerating universe has profound implications for the future of astronomy. Billions of years from now, astronomers in the merged Milkomeda galaxy will see a much emptier universe, with only a few nearby galaxies visible in their night sky. The rich cosmic web of galaxy clusters and filaments that we observe today will have disappeared beyond their cosmic horizon, for civilizations that might arise in the far future. The evidence for the Big Bang and cosmic evolution will be much harder to find. They will inhabit a cosmic island, isolated from the rest of the universe by the accelerating expansion of space itself. The cosmic microwave background will have cooled and redshifted beyond detection, erasing one of our most important clues about the universe's origin. The elegant spiral arms that define the Triangulum galaxy's beauty may be nothing more than a temporary cosmic pattern, destined to fade and reform in an endless cycle of creation and destruction that operates over hundreds of millions of years. Spiral structure represents one of the most persistent puzzles in galactic astronomy. If the spiral arms were simply material features rotating with the galaxy, they would wind up completely after just a few rotations, creating a tightly coiled spring rather than the open, elegant patterns we observe. The fact that spiral galaxies maintain their structure over billions of years suggests that something more complex is at work. The current understanding of spiral structure treats the arms as transient waves rather than permanent features. These spiral density waves propagate through the galactic disk like ripples on a cosmic pond, compressing gas and triggering star formation as they pass. The bright, young stars that illuminate the spiral arms are not permanent residents, but temporary markers of these passing compression waves. Computer simulations reveal that spiral patterns can be remarkably dynamic, strengthening and weakening over cosmic timescales. Some models suggest that spiral arms can form spontaneously from gravitational instabilities in the galactic disk, grow to prominence over tens of millions of years, then fade away as the driving instabilities dissipate. New spiral patterns can emerge from different instabilities, creating a constantly evolving galactic architecture. The number of spiral arms in a galaxy can change over time. Triangulum currently displays a two-armed spiral pattern, but this may not be its permanent configuration. Gravitational interactions with neighboring galaxies, the passage of massive gas clouds, or internal instabilities could alter the arm number and pattern, transforming the galaxy's appearance over cosmic time. The spiral pattern may also be influenced by the galaxy's bar structure, though Triangulum appears to lack the prominent central bar seen in many spiral galaxies. Computer models show that bars can drive spiral waves, creating and maintaining arm patterns through gravitational torques. The absence of a strong bar in Triangulum suggests that its spiral structure may be maintained by other mechanisms or may be less stable than in strongly barred galaxies. Recent observations have revealed that many galaxies show evidence of multiple spiral patterns operating simultaneously, with different arm segments having different pitch angles and rotation speeds. This suggests that spiral structure may be more complex and chaotic than simple density wave theory predicts, with multiple, overlapping patterns creating the observed morphology. The interaction between spiral arms and stellar feedback processes adds another layer of complexity. Massive star formation in spiral arms produces stellar winds and supernova explosions that can disrupt the very density enhancements that created the arms. This feedback can weaken spiral patterns over time, potentially erasing them entirely in regions of intense star formation. Environmental factors also influence spiral structure stability. Galaxies in dense clusters often lose their spiral patterns through interactions with the intracluster medium and neighboring galaxies. Triangulum's location in the relatively sparse local group may have helped preserve its spiral structure, but the upcoming merger with Andromeda and the Milky Way will certainly destroy its current pattern. The study of spiral galaxies at different redshifts has revealed that spiral patterns were less common in the early universe. When galaxies were smaller, more irregular, and had higher rates of mergers and interactions. This suggests that spiral structure may be a relatively recent development in cosmic history, emerging as galaxies settled into more stable configurations. Some theoretical models propose that spiral patterns undergo regular cycles of formation and dissolution, driven by the galaxy's rotation and internal dynamics. These cycles could operate on timescales of hundreds of millions of years, meaning that the spiral pattern we observe today may be just one phase in a long-term oscillation. Every cubic centimeter of space surrounding the Triangulum galaxy is filled with ancient photons from the universe's infancy, a cosmic background radiation that carries within it the fossilized imprint of creation itself. The cosmic microwave background represents the oldest light in the universe. Photons that began their journey when the cosmos was only 380,000 years old. At that moment, the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms, making space transparent for the first time since the Big Bang. The brilliant flash of this cosmic dawn has been traveling through space ever since, gradually cooling and stretching to microwave wavelengths. This ancient radiation bathes the Triangulum galaxy from all directions with nearly perfect uniformity, maintaining a temperature of just 2.7 degrees above absolute zero. The photons carry no memory of their 13-billion-year journey through space, arriving at Earth with the same intensity they had when atoms first formed in the primordial universe. Yet within this seemingly uniform background lie tiny temperature fluctuations, variations of just a few millionths of a degree that represent the seeds from which all cosmic structure grew. These quantum ripples in the early universe, stretched to cosmic proportions by inflation, provided the gravitational wells around which the first dark matter halos formed, eventually giving birth to galaxies like Triangulum. The cosmic microwave background serves as a cosmic baby picture, showing us the universe when it was smooth, hot, and filled with a nearly uniform plasma of protons, electrons, and photons. The slight density variations visible in this ancient light reveal the initial conditions from which 13 billion years of cosmic evolution would unfold. Every galaxy in the universe moves through this background radiation field, creating a slight Doppler shift that reveals cosmic motion on the largest scales. The Triangulum galaxy, along with the entire local group, is moving at over 600 kilometers per second relative to the cosmic microwave background, carried along by the gravitational influence of massive structures in the cosmic web. This motion creates a dipole pattern in the background radiation, with photons appearing slightly hotter in the direction of motion and cooler in the opposite direction. This cosmic speedometer allows astronomers to measure the local group's motion through the universe and map the large-scale gravitational fields that drive this cosmic flow. The polarization of the cosmic microwave background provides additional information about the early universe, revealing how photons scattered off electrons in the primordial plasma. These polarization patterns carry the signatures of gravitational waves from cosmic inflation. potentially providing direct evidence for the rapid expansion that occurred in the universe's first fraction of a second. As the universe continues to expand, the cosmic microwave background grows steadily colder and fainter. In the far future, this ancient radiation will cool to such low temperatures that it becomes virtually undetectable, erasing one of our most important windows into cosmic history. Future civilizations may lose access to this crucial evidence for the Big Bang and early cosmic evolution. The background radiation also provides a fundamental reference frame for the universe, defining a cosmic rest frame relative to which all motion can be measured. This frame is particularly important for understanding dark energy and cosmic acceleration, as it provides a standard against which the expansion history of the universe can be measured. Subtle interactions between galaxies and the cosmic microwave background can heat the radiation through inverse Compton scattering, creating slight temperature increases in regions where hot gas is present. These thermal signatures allow astronomers to map the distribution of hot gas throughout the universe and study the evolution of galaxy clusters. The Triangulum galaxy owes its existence to quantum uncertainty, born from microscopic fluctuations in the fabric of space-time that occurred when the universe was smaller than a single atom. In the first fraction of a second after the Big Bang, the entire observable universe was compressed into a region smaller than a proton, governed by the strange laws of quantum mechanics, where particles and energy exist in states of fundamental uncertainty. At these scales, the very notion of empty space breaks down, replaced by a seething foam of virtual particles and energy fluctuations that appear and disappear on timescales too brief to measure. These quantum fluctuations represented tiny variations in energy density, random patterns of slightly more and slightly less dense regions scattered throughout the primordial universe. Under normal circumstances, these microscopic ripples would have remained forever invisible, too small to influence the macroscopic world. But the universe was about to undergo a transformation that would amplify these quantum whispers into cosmic shouts. Cosmic inflation, a period of exponential expansion lasting perhaps 10 to the minus 35 seconds, stretched these quantum fluctuations to astronomical scales. Regions that were once separated by distances smaller than the width of a proton suddenly found themselves separated by light years. The tiny energy variations that existed on quantum scales became density fluctuations spanning vast cosmic volumes. When inflation ended, these amplified quantum fluctuations provided the seeds for all future cosmic structure. Regions that were slightly denser than average had stronger gravitational fields, allowing them to attract additional matter and grow even denser over time. This process of gravitational amplification operated over billions of years, transforming tiny quantum ripples into galaxies, galaxy clusters, and the cosmic web itself. The Triangulum galaxy began as one of these quantum fluctuations, a microscopic density enhancement that existed when the universe was incomprehensibly young and small. The matter that would eventually form its hundreds of billions of stars was initially spread over a vast region of space, held together only by the gravitational memory of that primordial quantum fluctuation. Computer simulations can trace the evolution of individual quantum fluctuations from the end of inflation to the present day, showing how microscopic variations in the early universe grew into the massive structures we observe today. Each galaxy represents the culmination of nearly 14 billion years of gravitational evolution, all tracing back to quantum uncertainty in the universe's first moment. The statistical properties of these quantum fluctuations have been precisely measured through observations of the cosmic microwave background, revealing that they follow a nearly scale-invariant spectrum predicted by inflation theory. This remarkable agreement between quantum mechanics and cosmological observations provides strong evidence that our understanding of the early universe is fundamentally correct. Different types of quantum fluctuations may have contributed to cosmic structure formation. Scalar field fluctuations associated with the inflaton field that drove cosmic expansion created the density variations that became galaxies and galaxy clusters. Tensor fluctuations, representing gravitational waves from the inflationary epoch, may have left their signatures in the polarization patterns of the cosmic microwave background. The quantum origin of cosmic structure connects the smallest scales of physics to the largest scales of astronomy, demonstrating that quantum mechanics is not just a laboratory curiosity, but a fundamental principle that shapes the entire universe. The galaxy we inhabit exists because of the inherent uncertainty built into the quantum vacuum itself. Some theories suggest that the multiverse concept may emerge naturally from quantum fluctuations during inflation, with different regions of space experiencing different amounts of expansion and ending up with different physical properties. In this view, our observable universe may be just one bubble in an infinite cosmic foam of parallel universes. The Triangulum galaxy does not exist in isolation, but is embedded within the largest structure in the universe. A cosmic web of dark matter filaments that connects galaxies across billions of light years in an intricate network of matter and energy. This cosmic web represents the universe's fundamental architecture, a three-dimensional scaffolding built from dark matter that formed over billions of years of gravitational evolution. Like a vast spider web stretched across space, the cosmic web consists of dense filaments separated by enormous voids, creating a foam-like structure that extends throughout the observable universe. The filaments themselves are highways of dark matter and gas that channel material from the cosmic voids into dense nodes where galaxies form and evolve. These cosmic arteries can stretch for hundreds of millions of light years, connecting distant galaxy clusters in a network that spans scales larger than any single astronomical object. The Triangulum galaxy sits within one of these filaments, part of the local group's position in a relatively dense region of the cosmic web. The gravitational influence of this large-scale structure has shaped the local group's evolution, determining which galaxies became gravitationally bound and how they have interacted over cosmic time. Galaxy formation within the cosmic web follows a hierarchical pattern, with the largest structures forming at the intersections of multiple filaments. These cosmic crossroads become the sites of massive galaxy clusters, gravitational wells so deep they can trap thousands of galaxies and vast quantities of hot gas. The local group occupies a more modest position in this hierarchy, located along a smaller filament rather than at a major intersection. The cosmic web's filamentary structure traces the underlying dark matter distribution, which began forming shortly after the Big Bang, when tiny density fluctuations in the early universe began to grow under their own gravity over billions of years. These fluctuations evolved into a network of dark matter halos connected by streams of matter flowing along the web's filaments. Gas follows the dark matter, flowing along filaments toward the dense nodes where galaxies form. This cosmic plumbing system has operated throughout the universe's history, feeding galaxies with the raw materials needed for continued star formation. When gas flows along filaments are disrupted or cut off, galaxies can become starved of fuel and cease forming new stars. The cosmic web also determines galaxy properties through environmental effects. Galaxies in dense filaments and cluster cores experience ram pressure stripping, tidal interactions, and other processes that can remove their gas and halt star formation. Galaxies in cosmic voids, far from major filaments, may evolve in relative isolation, with different star formation histories. Computer simulations reveal that the cosmic web has a fractal-like structure, with smaller filaments branching off from larger ones in a hierarchy that extends down to galactic scales. This self-similar structure emerges naturally from gravitational collapse and reflects the scale-invariant nature of the initial quantum fluctuations that seeded cosmic structure. The local group's motion through the cosmic web is influenced by the gravitational pull of massive structures like the Virgo cluster and the Great Attractor, enormous concentrations of matter that exert their influence across hundreds of millions of light years. This cosmic flow carries the local group at speeds exceeding 600 kilometers per second relative to the cosmic microwave background. Dark energy's acceleration of cosmic expansion is gradually stretching the cosmic web, making filaments longer and thinner while enlarging the cosmic voids. This process will eventually disconnect distant parts of the web, isolating galaxy groups like the local group from the larger cosmic structure as space itself expands between them. Across the next 100 trillion years, every star in the Triangulum galaxy will live out its destined evolution, transforming the cosmos from a brilliant tapestry of stellar light into a graveyard of cooling remnants drifting through an ever-expanding darkness. The stellar era that has defined the universe for the past 13 billion years represents just the opening chapter in cosmic history. The most massive stars in Triangulum, those brilliant blue giants that burn with the intensity of millions of suns, will exhaust their fuel first. Within just a few million years, they will explode as supernovas or collapse into black holes, adding to the galaxy's growing population of stellar corpses. Medium-mass stars like our Sun face a different fate, burning steadily for billions or even trillions of years before swelling into red giants and finally shedding their outer layers as planetary nebulae. The white dwarf cores they leave behind will shine with stored thermal energy for tens of billions of years, gradually cooling from white-hot to red, then brown, then black as they radiate their heat into the cosmic void. The smallest stars, red dwarfs with masses less than half that of our Sun, will outlive all others. These cosmic misers burn their hydrogen fuel so slowly that they can maintain nuclear fusion for over 100 trillion years, thousands of times longer than the current age of the universe. They will be the last stars shining when the galaxy finally goes dark. As stellar evolution proceeds, the galaxy's character will change dramatically. The brilliant blue and white stars that currently illuminate the spiral arms will vanish first, leaving behind populations increasingly dominated by cooler, redder stars. The galaxy's overall brightness will fade steadily as its most luminous members burn out and are not replaced. Star formation itself will gradually cease as the galaxy exhausts its reserves of star-forming gas. Stellar winds, supernova explosions, and galactic outflows will blow away much of the remaining interstellar medium, while the rest will be locked up in long-lived stars or stellar remnants. Without new stars being born, the galaxy will begin its slow fade into darkness. The merger with Andromeda and the Milky Way will accelerate this process by triggering a final burst of star formation that quickly consumes the remaining gas reservoirs. The resulting elliptical galaxy will have few young stars and little ongoing star formation, representing the end of the galaxy's active phase of stellar birth and evolution. Over cosmic time, even the longest-lived stars will eventually die. When the last red dwarf finally exhausts its fuel in the far future, the stellar era will end, replaced by an epoch dominated by brown dwarfs, white dwarfs, neutron stars, and black holes. These stellar remnants will continue to interact gravitationally, but they will no longer produce the nuclear fusion that has powered cosmic evolution for eons. Brown dwarfs, failed stars that never achieved the temperatures needed for sustained nuclear fusion, will experience a brief moment of glory as the universe cools around them. These cosmic embers may actually become warmer than their surroundings for a time, making them some of the most active objects in the post-stellar universe. White dwarf stars will undergo their own slow evolution, crystallizing into cosmic diamonds as they cool over trillions of years. Some white dwarfs in binary systems may experience thermonuclear explosions when they accrete matter from companions, creating brief supernovas in an otherwise dark galaxy. These events will become increasingly rare as binary systems evolve and separate. Neutron stars will continue their cosmic lighthouse behavior, sweeping beams of radiation across space as they rotate. But even these will eventually slow down and fade as their rotational energy dissipates. The radio pulsars that currently serve as cosmic timekeepers will gradually fall silent, their beams weakening until they can no longer be detected. Black holes will become increasingly dominant as other objects fade. They will continue to grow by accreting matter and merging with each other, creating ever more massive black holes that will ultimately dominate the galaxy's gravitational field. These cosmic vacuum cleaners will slowly consume the galaxy's remaining matter over timescales that dwarf even the stellar era. The process of stellar evolution will also be influenced by the expanding universe itself. As space continues to expand under the influence of dark energy, the galaxy will become increasingly isolated from its cosmic environment. The background temperature of the universe will continue to drop, eventually falling below the temperature of the coolest stellar remnants. In this far future, the distinction between hot and cold will reverse. Black holes, which currently appear cold against the cosmic background, will eventually become the warmest objects in the universe as everything else cools toward absolute zero. Their Hawking radiation, currently undetectable, will become the primary source of energy in a universe that has otherwise reached thermal equilibrium. In the unimaginably distant future, the Triangulum galaxy and all cosmic structures will succumb to the inexorable march toward maximum entropy, dissolving into a universe of perfect equilibrium where no energy flows and no processes can occur. The heat death of the universe represents the ultimate expression of the second law of thermodynamics on cosmic scales. Just as a hot cup of coffee inevitably cools to match room temperature, the universe is gradually evolving toward a state where all matter and energy reach the same temperature and no further work can be performed. This cosmic equilibrium will mark the end not just of stars and galaxies, but of time itself as a meaningful concept. The journey toward heat death begins with the accelerating expansion driven by dark energy. As space continues to expand exponentially, galaxies will be carried apart faster than light can travel between them. The observable universe will shrink to encompass only the local group and its immediate neighbors, creating cosmic islands of matter separated by vast expanses of empty space. Within these isolated regions, gravity will continue to operate, gradually pulling matter together into increasingly massive black holes. Stars will be torn apart by tidal forces as they spiral into these cosmic drains, while planets and asteroids will follow similar fates over unimaginably long timescales. Eventually, each galactic remnant will collapse into a single supermassive black hole containing all the matter that once formed billions of stars. But even black holes are not eternal. According to Stephen Hawking's theoretical calculations, black holes slowly evaporate through quantum effects at their event horizons, emitting radiation and gradually losing mass over timescales that dwarf the current age of the universe. A black hole with the mass of our Sun would take longer than 10 to the 67th power years to evaporate completely, a time so vast that it defies human comprehension. The supermassive black holes that will eventually consume entire galaxies will persist even longer, their evaporation times extending to 10 to the 100th power years or more. During this unthinkably long epoch, these black holes will be the only remaining sources of energy in an otherwise dead universe, slowly radiating their mass away as Hawking radiation until nothing remains. As black holes evaporate, they will populate the universe with a thin soup of elementary particles, photons and neutrinos. These particles will spread throughout the expanding space, their density decreasing as the universe grows larger and larger. Eventually, the expansion will carry particles so far apart that they rarely interact, creating a cosmos of infinite size but negligible density. The temperature of this final state will approach absolute zero, limited only by the cosmic microwave background radiation that will continue to cool as the universe expands. In this cold, dark future, no complex structures can form or persist. There will be no stars, no planets, no life, and no observers to witness the cosmic silence. Even protons, the building blocks of atomic nuclei, may not survive forever. Some theories of particle physics predict that protons will decay with half-lives of 10 to the 34th power years, eventually dissolving all atomic matter into leptons and photons. If proton decay occurs, it will accelerate the universe's journey toward maximum entropy by eliminating the last vestiges of complex matter. The concept of heat death raises profound questions about the nature of time and causality. In a universe at perfect thermal equilibrium, no events can occur because there are no energy gradients to drive processes. Time becomes meaningless when nothing changes, leading some physicists to speculate that time itself may end with the universe's thermal death. Yet, even in this seemingly hopeless scenario, quantum mechanics may offer escape routes. Random quantum fluctuations in the vacuum could spontaneously create pockets of order within the cosmic equilibrium, potentially giving rise to new universes through quantum tunneling events. These quantum fluctuations might even recreate entire galaxies or civilizations, though the waiting times would be incomprehensibly vast. Our journey through the Triangulum galaxy ends where all great explorations must not with answers, but with deeper questions that stretch the boundaries of human understanding and point toward mysteries we have only begun to imagine. We began with a galaxy that spins impossibly fast, held together by invisible dark matter in defiance of everything we thought we knew about gravity and motion. We witnessed stellar giants that live fast and die young, their violent deaths seeding space with the elements needed for life. We discovered rogue black holes wandering through the darkness, cosmic architects painting nebulae in impossible colors, and ancient stars that preserve the memory of the universe's violent youth. Along the way, we encountered forces and phenomena that challenge our most fundamental assumptions about reality. Dark energy accelerates the expansion of space itself, driving galaxies apart in a cosmic dance that began with quantum fluctuations smaller than atoms. Gravitational waves ripple through the fabric of space-time, carrying messages from collisions so violent they shake the universe itself. Magnetic fields, invisible to our senses, weave through every corner of the galaxy, creating highways for cosmic rays that race at nearly the speed of light. The galaxy revealed itself to be far more than a collection of stars spinning in space. It is a complex ecosystem where matter and energy flow in cycles that span billions of years. Gas condenses into stars. Stars forge heavy elements and explode, their deaths triggering new episodes of stellar birth in an endless dance of creation and destruction. The galaxy breathes, pulsing with rhythms we are only beginning to understand. We discovered that the galaxy does not exist in isolation, but is part of a cosmic web that connects all of space in a network more vast and complex than any structure we can imagine. Dark matter filaments stretch across billions of light years, channeling matter and energy in patterns that echo the quantum fluctuations of the universe's first moment. Yet, for every question our journey answered, it raised 10 more. What is dark matter? And why does it outweigh everything we can see by such an enormous margin? What force drives dark energy's acceleration of cosmic expansion? How do black holes really work? And what happens to information that falls beyond their event horizons? Are we alone in this vast cosmic theater? Or do other forms of consciousness gaze upon the same stars we study? The search for life in the universe has only intensified as we've learned more about the galaxy's complexity. With hundreds of billions of stars and potentially trillions of planets, the Triangulum galaxy represents an almost infinite laboratory for the emergence of life. The heavy elements forged in stellar cores provide the building blocks for rocky worlds and complex chemistry. The galaxy's magnetic field may help shield planetary systems from deadly cosmic radiation. But life as we know it requires more than just the right elements and conditions. It needs stable environments, protection from cosmic violence, and perhaps most importantly, time. The galaxy's future collision with Andromeda will disrupt any civilizations that might have emerged in its spiral arms. The gradual fate of stellar evolution will eventually eliminate the energy sources that complex life requires. Yet, even as we contemplate these cosmic endings, new possibilities emerge. Perhaps life will learn to harness energy from black hole evaporation, or to manipulate the quantum vacuum itself. Perhaps consciousness will find ways to spread throughout the cosmic web, creating networks of intelligence that span galactic distances. Perhaps the heat death of the universe is not an ending, but a transformation, a gateway to forms of existence we cannot yet imagine. The tools and techniques that revealed the Triangulum galaxy's secrets continue to evolve at a breathtaking pace. Gravitational wave detectors are opening entirely new windows onto cosmic violence. Space telescopes are peering deeper into space and time than ever before. Computer simulations are revealing how quantum fluctuations grew into galaxies, how dark matter shapes cosmic evolution, and how the universe might evolve over timescales that dwarf human history. Each new discovery seems to make the universe both more comprehensible and more mysterious. We understand how stars work, but stellar nurseries still surprise us with their complexity. We can trace the evolution of galaxies over cosmic time, but dark matter remains as enigmatic as ever. We can detect gravitational waves from black hole mergers, but we still don't know if black holes destroy information or preserve it in forms we haven't discovered. The Triangulum galaxy has served as our guide through this cosmic mystery tour, but it represents just one galaxy among hundreds of billions in the observable universe. Each galaxy tells its own story, shaped by unique combinations of dark matter, stellar evolution, and cosmic environment. The diversity of galactic forms and behaviors suggests that the universe is far richer and more varied than any single example can reveal. As our cosmic journey ends, we return to the fundamental truth that began our exploration. The universe is under no obligation to make sense to us. It exists according to laws we are still discovering, operating on scales of space and time that stretch human comprehension to its limits. Yet, somehow, in this one small corner of one ordinary galaxy, matter has organized itself into forms capable of contemplating the cosmic whole. The greatest mystery of all may be consciousness itself, the emergence of awareness from stellar ashes, and the ability of the universe to know itself through minds like ours. We are the galaxy's way of understanding itself. Cosmic archaeologists decoding the history written in starlight and gravitational waves. Our journey through the Triangulum galaxy concludes, but the adventure of cosmic discovery continues. Each question answered reveals new frontiers to explore, new mysteries to unravel, new wonders to contemplate. In the vast cosmic dark, we have become the light.